extinct. The very word is chilling. It means that a species no longer survives in this world. Already there have been 5 great extinction events in the history of our planet. What if the next species to be obliterated were us? We pay scant regard to the planet-sized mechanism churning below our feet and over our heads. We are, after all, the apex species of planet Earth. We flourish, we consume, and we drive the natural world to oblivion. Only when a dramatic event strikes, earthquake, eruption, tsunami, are we reminded of nature's awesome force. Sometimes, for reasons we shall explore, Earth and the species on it come to blows. Are we next to be knocked out? History teaches us only what to expect. We have at least those 5 catastrophic planetary events to learn from, if we are to avoid a human calamity.
The Earth has suffered 5 great mass extinction events, and this has been since the last 500 million years. These have been dubbed the Great Five, or the Big Five.
The first recognized one is the end Ordovician mass extinction, which brought to an abrupt halt sort of a big diversification event where lots of new groups evolved.
It's not known whether there were really any plants at all on land before that.
And it's now thought that the main reason this happened was a massive ice age, a very brief, probably less than 1 million years in length. For comparison, our current ice age that we're in has lasted for at least 2.5, possibly 5 million years. So this was very brief and very sharp. So sea levels fell very quickly, lots of environments were lost, and then it ended abruptly again. Sea levels rose again, so it caused more disruption.
Certainly after that, we've got evidence, hard evidence of pollen from the land, and even some insects and things showing that life had moved out onto the land during the late Ordovician and into the Silurian. But after that, soon after that, they actually started to evolve into large trees during the Devonian, late Silurian and into the Devonian. And so there are what we see today known as lycopods, or club mosses, little moss-like things that live near water still. And today they're quite small, but they were able to grow into these large trees, the first large trees and first forests. And these forests actually altered, we have evidence they altered the carbon cycle. Because these large trees were able to grow across the empty landscapes, their roots dug down into the soils and they caused extreme erosion. And so the soils were actually then washed away into the oceans, and this changed the whole carbon cycle.
The next one was the late Devonian mass extinction. In that case, it appears that lots of the ocean just suffocated, basically. There were things going on that caused the ocean to lose a lot of its oxygen. Possibly newly evolved land plants caused a lot more erosion by digging in their roots and causing nutrients to run off, causing algal blooms, which sucked oxygen out as they decayed.
And a lot of evidence does point towards these significant changes on the land and to the carbon cycle as being one of the primary drivers of the mass extinction.
And so the ocean floors became sort of dead zones, and there were several pulses. It wasn't just one individual event. So this spread out over millions of years, quite different to the previous one, as I mentioned.
It's hard for people to really imagine this, but there are more types of animals in the past than there are today. So even right before the dinosaurs at this point in time, we're talking about the Permian, right before the biggest extinction event ever, the Permian-Triassic mass extinction, there were huge diversities of different types of animals and really complex so-called ecological tiering as well. arguably as complex as today. And people don't realize that there were just so many more different types of animals. And with each subsequent extinction, we keep losing body plans. So as today, if we're on the verge of another great extinction, we can actually show in the past that this has happened, where we lose all these body plans. And there are some organisms which are really rare today, and they're on the brink of extinction. And we can actually see we're going to lose major body plans again unless they're conserved. But we can actually look and learn a lot from the fossil record to show what actually can happen after a mass extinction and how the world changes or can change.
The largest mass extinction event ever to occur almost entirely wiped life from Earth.
The greatest extinction event to ever strike the Earth occurred about 252 million years ago. This is called the Great Dying, but it's at the Permian-Triassic mass extinction boundary. So at this point in time, as far as we know from all of the fossil studies that have been done in terms of all the geologic sections around the planet, on land and in the sea, we know that the extinction magnitude was on a scale that we just really can't imagine, at about 95% of all life on the planet becoming extinct.
It was the only mass extinction that affected insects, as far as we know. The other ones seem to not affect insects as much. And it's thought to probably be caused by a whole combination of events that caused a perfect storm of bad environments. So you had things like a major greenhouse event spike, place warmed by up to 10 degrees very quickly, possibly multiple times. There's even the thought that a new type of bacterium evolved that was able to decompose carbon on the seafloor and turn it into methane, which is a powerful greenhouse gas.
So this affected the carbon dioxide in the atmosphere, and there's also a lot of acids and toxins released into the atmosphere. So this would have really affected the life on the land, and particularly the plants themselves. So these huge forests were actually wiped out at this time.
And probably a lot of hydrogen sulfide came out of the oceans because they were stagnating, and hydrogen sulfide is quite a toxic gas, and it caused a lot of things to maybe die out from that. And that took a long time to recover from. There was sort of what's known as a coal gap, meaning there were no forests for about 5 million years, and a coral gap, which means there were no reefs in the oceans for a long time, and the oxygen levels in the atmosphere plummeted from something close to about 30% in the atmosphere compared to today's 21%, possibly dropping down to 10%. So that's like being on Mount Everest, basically, at seafloor in terms of the oxygen density. As for the big dying, that's more complicated because it was such a bad environment for such a long time that was caused by these various factors, and we can see in the fossil record that there's the climate seemed to just fluctuate wildly for a good 5 million years after the mass extinction. So species that survived that initial dying still had to weather all these big changes that came afterwards, and it seems like a lot of the ones that survived were generalists. So we say today, if there's another catastrophe, it'll be the rats and the seagulls and the cockroaches that will survive. And they are quite good generalists. They can survive on just about anything. They're not specialized to any particular food, and they have rapid breeding cycles as well, which helps. So things like, say, an elephant that has a long breeding cycle, they might not survive so well, and only few offspring. And that seems to be the pattern back then as well. But there are other groups that seem to have weathered previous environmental changes that were knocked out.
Some organisms, such as the seafloor scavenging trilobites, survived numerous extinction events.
One of the most successful organisms in the sea were the trilobites, which were a type of arthropod. They were successful for several 100 million years. They evolved in the latest Precambrian, as far as we know, so that we're talking about 550 or so million years ago, but they were extremely successful in the sea for various reasons. They also replaced several organisms that were really diverse, such as the so-called cup animals or archaeocyathids, okay, which disturbed their habitats, and basically there was an arms race at this time.
So probably trilobites are in the top 3 groups that people know about when you talk about extinct things, just after the dinosaurs and the ammonites. They certainly were one of the very first groups that were quite dominant in the oceans, thousands of species right early on. Some of the very best eyesight with their compound eyes and a lens made out of a crystal of calcite, quite amazing, the only animal to ever do that. But they had weathered many different events, including, I assume, various different apex predators coming in from initially large nautiloids and then to the sea scorpions and then the armor-plated fish, and they seem to weather all of those with all these defenses, very spiny. But at the end, Devonian extinction events, they were heavily impacted, and almost none of them made it through except for one small group that sort of still struggled on until finally getting wiped out in the Permian. So they were almost all bottom dwelling on the ocean floor, really reliant on the sea floor. So you have the legs, you can sometimes see their tracks where they shuffled up the sediment and they ate the animals and other creatures that lived in the sediment. So if the seafloors were really starting to die and nothing sort of lived there, their whole food chain collapsed. So that, I'm assuming, is a major reason why they just couldn't quite make it through. They were heavily reliant on the seafloors being full of oxygen and full of life. It's quite sad because they're very cool animals. I mean, such a diversity and beautiful shapes.
One adaptable organism survived the Great Dying. Lystrosaurus went on to become the ancestor of dinosaurs and mammals alike, including humans.
So during the Permian in Pangaea, we know from the fossil record that there were high diversities of tetrapods, so 4-legged organisms like this guy here, which is called Lystrosaurus. For some reason, it had attributes that enabled it to cross this boundary relatively unscathed. So we know by looking at the skeleton, it probably did scavenge. It had a barrel chest in terms of air capacity as well. We know that the air was probably fairly thin. It was basically life under a green sky, very different from today because of the hydrogen sulfide gas. Very few other organisms persisted across this boundary. And of course, these were very important tetrapods because they evolved eventually into mammals, okay, including us. In terms of recovery, we estimate that it took about 100 million years for the ecosystems to recover after that mass extinction.
And then not too long after, I guess, a few tens of millions of years later, the end Triassic extinction occurred. It's possibly one of the most mysterious ones because I think there's fewer causes that have been identified for it, but it might again be big volcanic eruptions that caused big climate changes to occur massively.
Volcanism can have amazing impacts on climate and the environment in several different ways. So first of all, if you have a big volcanic eruption, there's lots of dirt and dust and chemicals that get added to the atmosphere. One part of those are sulfide oxides or maybe even hydrogen sulfides. And these can, first of all, form sulfide aerosols. These are really tiny particles that actually get into the really high atmosphere, and they can stay there for a long time. And by doing so, they will shield the atmosphere. It's like a blanket. So incoming solar radiation actually doesn't get quite through, and it becomes cold for a few days, months, maybe even years if it's a big eruption, and it becomes darker. If it's a really big eruption, it might even become so dark that photosynthesis becomes a problem.
Well, a lot of people think that the Triassic was pretty much a stressed environment throughout, largely due to the oxygen levels in the atmosphere remaining really low. So the oxygen levels in the Carboniferous to Permian, it's the big ice age there, had gone up to 32%, which is massive, like compared to 21% today, and largely due to the big growth in terrestrial forests that had evolved, and it allowed all sorts of things to evolve, giant insects. Towards the late Permian, even before the mass extinction, oxygen levels really started dropping, and indications are that in the early Triassic, oxygen levels stayed close to 10 or 12%, which is half of what we have today. It's really quite extremely low. And it seems that they didn't really get up to closer to modern levels again until into the Jurassic, after the mass extinction at the end of the Triassic. But the interesting thing about it is that it probably encouraged some groups to evolve really efficient breathing. So if you think about the birds today, they have circular breathing. They don't really have to breathe in and out as much as they just have they have lots of air pockets to really get the oxygen out. And that might be a legacy of the early dinosaur ancestors evolving in the Triassic to deal with these low oxygen levels. So that stressed environment had some unintended consequences later, which is why we see such success in the birds today, able to fly, which is high oxygen demand. After that, we have the big golden age of the dinosaurs that lasted for a long time until it was brought to the end by the most famous, popularly famous extinction, the dinosaur extinction at the end of the Cretaceous.
In fact, we now can date it to about 66.03 million years ago.
Famously, there was a big asteroid impact, probably the biggest asteroid impact in the last 500 million years.
So we're talking upwards of maybe even 1 trillion tons of rock just hurtling through space, heading towards our Earth. And when it did actually reach our Earth, it would have gone through the atmosphere within a fraction of a second, and it hit the Earth, created a hole that was probably about 30 kilometers deep, and we know about 180 to 200 kilometers wide.
So that alone is pretty bad. But there was also indication that there was a lot of greenhouse gases being emitted by these big volcanic eruptions, continent-wise eruptions in India that caused greenhouse spikes, and we can see that in animal populations that were pretty stressed already before the asteroid hit.
Any organism even close to it would have been basically incinerated from the fireball. So this again had this effect where it affected the base of the food chain because there was a dust cloud that enveloped the Earth. So it affected plants at the base of the food chain, and again we had this propagating effect all the way up through to the apex predators.
So the asteroid might have just been the last bad news for all of life, and it caused the non-avian dinosaurs to die out, but many other groups went as well at the same time.
So in our extinction story, it's really important to differentiate between background extinction and mass extinction. So when we actually look at background extinction rates, we can compare the modern to the fossil record. So we can actually delve into the geologic past by looking at organisms. And what we see, which is really important, is that, for example, if we look at mammal fossils, probably one mammal species per 1,000 years became extinct. So that's background extinction. If we look at the present day, we estimate that in relative to background extinction rates, the extinction rate today is something on the order of about 1,000 times what it is if we look at the fossil record.
Coming from a background of geology and looking into deep time, it's been quite well established that there is a clear, solid link between carbon levels, especially carbon dioxide levels in the atmosphere, and climate. Now, it's not always the carbon dioxide that causes the climate change to start with, but it's either the first thing that change in carbon dioxide up or down is very closely associated with massive climate change. So sometimes the carbon dioxide changes ahead of time, so things like massive volcanism can cause warming. In some cases, like the Ordovician extinction, big mountain building, that weathering actually draws carbon dioxide out of the atmosphere, and that causes the carbon dioxide to plunge, which is what probably happened there, causing an ice age. At other times, it can be other causes, like the Earth's orbit can change its shape. It regularly does that in a predictable way. And then those changes from the sun's radiation causes a start in shift towards warmer or colder, but then that initiates sort of a feedback with the carbon dioxide. So the warmer it gets, often the carbon dioxide goes along, starts going up as well, which causes more warming, which causes more carbon dioxide. So carbon dioxide either initiates the warming or cooling, or it exacerbates the change. And the quicker it changes, the more rapidly the climate changes. And rapid climate change often leads to species not being able to adapt quick enough. And if the environments shift too fast for specialized species, they die out. And if that goes above what we call background extinction rates, we start seeing sort of the clear markers of mass extinctions. And there is the thought that at the moment the change is exceeding the rate at which species can sort of adapt. And it's not like with all the other mass extinctions, it's probably more a perfect storm of conditions, not just one like climate change or an asteroid, but a host of things. So we have not just climate change induced by humans at the moment, but we have deforestation or urban sprawls or habitat fragmentation, things like that, that are stopping species from adapting at a fast enough rate. So it's worrying to see where we're heading, knowing what's happened in the past.
It's really important that we actually understand these species and the effect that we're having with all this deforestation and other things that are happening around the planet, which is also affecting climate. Because another factor which affects species as well is, in fact, some groups of organisms are very controlled by temperature, and even the slightest increase in temperature can affect their distribution and actually make their populations dwindle through time. So there are various important factors, and these factors that control species through time relate to ecosystem energy supply. They relate to climatic events as well. So various aspects of climate, which are quite diverse when we talk about them. It could actually mean about where they live. To live on a seafloor in terms of bathymetry. There are depth constraints as well with sea level rise and fall. That really affects them as well. So there's a huge number of parameters that affect a species through time and space, which are important to consider. And with so many species becoming extinct, we know that there's a massive problem in the environment.
Yeah, the ecosystems, particularly the rainforests in South America and the Amazon or across Indonesia, have been severely affected, not just by the changes in carbon dioxide, but initially by clearing. And we also have our own very special rainforests that are extremely diverse up in the north of Queensland, and also an extremely diverse flora called the fynbos in both Africa and southwestern Western Australia. So these are extremely diverse biomes, and they're already showing significant extinctions as a result of both clearing and changes in the carbon dioxide levels that we've seen, which have been significantly greater in the last 50 years.
one of the groups that always gets raised as, well, how did they survive but the others didn't, is things like crocodiles and alligators. They've been around for longer than the dinosaurs and they're still around. And the recent massive freeze in Florida brought up some interesting images of crocodiles or alligators there basically poking their snouts through the ice and getting frozen in and going into a hibernation state. And so if you think about in this case, the mass extinction at the end of the dinosaur age, the Cretaceous, where there was probably almost a nuclear winter from the impact, that was probably a perfect way for them to survive that, where there was no food around for many years. So they had some ability to just weather it, whereas maybe some more active species, like the sort of warm-blooded early birds, a lot of the dinosaurs that needed a lot of food, the big ones, they just couldn't weather it out for all those years.
If we pay attention to it, one other event provides a lesson in carbon dioxide absorption in the oceans, the Paleocene-Eocene thermal maximum.
The Paleocene-Eocene thermal maximum, which is a mouthful, we usually call it PETM, was a very abrupt, short warming event that happened about 55 million years ago. Atmospheric temperatures rose by 5 to 8 degrees. And what is interesting is that it's actually one of the biggest mass extinctions in the deep ocean. And that's unusual because usually living conditions in the deep ocean are quite constant and we much more rarely see big mass extinctions there. So what we know is that this event was caused by a massive release of carbon into the atmosphere. There's still some controversy about where this carbon came from. It might have been enhanced volcanism, it might have been methane hydrates. But certainly this release happened fast on a geological timescale. We now pretty much think that this release happened at a much slower rate than what we see today, about at least 10 times, if not 100 times slower. And that has interesting implications because if you add CO2 into the atmosphere, the CO2 will be absorbed by the oceans. And when the ocean absorbs this carbon dioxide, actually carbonate ions get depleted in the ocean. And that's bad news for any organism that lives in the ocean that builds shells out of calcite or aragonite because they need these carbonate ions to actually build their shells.
Calcification rates, the way that the animals build up their shells with calcium carbonate, has dropped. There are things that are becoming thinner in their shells, which makes them more susceptible to other stresses, and that's just an additional problem for them. So climate change by itself isn't the whole story. The acidification is a big issue, and it has been in past extinctions as well. You can see the effect of the ocean acidification in those mass extinctions in the past, where shells get more less stable and things like that. And the expansion of ocean dead zones is a big story at the moment as well, where they've increased fourfold from what we knew maybe 50 years ago. So those dead zones, as I've said from other extinction events, are a big part of the stressors in these mass extinction events, and they're undoubtedly occurring.
So the Paleocene-Eocene thermal maximum was this unbelievable period in Earth history when the Earth really warmed up around the whole globe at temperatures that we haven't seen for a very long time. So there were crocodiles living in the Arctic. There were forests, and they're still preserved. You can burn the wood from those forests from 80 degrees north latitude. Like the whole planet was a different place. And it shows us that climate change is part of Earth history. It's a natural part of Earth history. The difference, though, is that even that enormous temperature change, that whole change in the Earth climate system, occurred naturally over a relatively long period of time, millions of years. The difference with today is that change is on the order of tens of years. It's happening so fast that the natural systems are out of balance. And that's a real challenge, not just for us, but actually for most living things on the planet.
I think it's uncontroversial that human activity of one form or another, even without the climate change, is causing things to go extinct. And that's been documented for many things over the last couple of hundred years. Big mammal groups that used to be massively abundant are gone. So how much is really going extinct is very hard to tell, because it would take half the population of the world to do sort of ecological surveys almost every year just to keep an eye on how things are doing. There's obviously not those resources. So as a paleontologist, it's easier because it's all the experiments been done. You can look at the fossil record, as imperfect as it is. Things that are happening right now are hard to really definitively say. But I would say that in the oceans especially, things like ocean acidification, where the raising of the carbon dioxide levels in the ocean waters, where most of the carbon dioxide is going at the moment, that little bit of acidification, which is not that little, it's gone by 2 decimal points, which is about a rise of well over 30% in acidity, really, because it's a logarithmic scale.
I think the fossil record tells us about events that have occurred in the past where carbon dioxide has run away in terms of quantity in the atmosphere. We've also seen, often coinciding with that, those toxic gases, release of methane, and all of these events have had dire consequences for ecosystems on the land and also in the ocean.
In terms of sea level rise, all of the ice volume, a lot of ice is being melted currently with the glaciers in the north and also in the southern hemispheres. So big changes are happening in the environment, but they're happening very quickly, and that's one of the big issues that humans are facing today.
Well, if left unchecked, we know for sure that temperatures will continue to rise, CO2 will continue to rise, acidification will continue and become much more severe. I think we already see the impacts right now. Lots of ecosystems really struggle to keep up with these changes. And when temperatures change, then animals or plants might be able to migrate to higher latitudes, but maybe not fast enough. Maybe there will be whole new ecosystem structures that will need to be established. Ocean acidification is if oceans become too acidic to sustain certain life. Other winners, other disaster taxa, as we call them, will certainly survive, but it will be a very different world. So sea level rise is due to 2 different physical mechanisms. One is, of course, melting ice caps, and we see this happening right now. Greenland is melting. Antarctica is starting to melt more than we actually initially thought. So there's certainly some tipping points there, because once an ice sheet starts to melt, it will continue to melt due to other feedback set. So when an ice cap starts to melt, it becomes less high. The lower it gets, the warmer it gets. You know, when you go up a mountain, the higher you get, the colder it gets. So just due to this change in height, it will start to melt faster. Also, the surface will become maybe a little bit darker because there's not much more snow accumulation. There will be more dust and other things that actually go on the surface. And especially regions where it starts to melt completely, what was white before will be replaced by rock or by whatever is underneath. These colors are much darker. They will absorb more incoming solar radiation and will become warmer. So there's several positive feedbacks that kick in once an ice sheet starts to melt. If we start to warm up our oceans, the water in the ocean will expand. And due to this expansion, we will experience sea level rise.
Oh, listen, people have been doing models for the last 20 years on, changes to the environment that are ongoing at the moment. And every time they produce a model, they have to revise it because the natural system is going faster than they modeled. So the Arctic ice, for example, that's down to about 1/3 of its size. That was only 20 years ago. And so these systems are changing incredibly quickly. The danger is that we have this enormous system called the ocean that absorbs a huge amount of energy because it's so big. But once that reaches a tipping point and we start melting the ice and temperatures start to rise faster than they are now, which we know will happen, all the models show that, then we're in uncharted territory. And those changes are very hard to adapt to.
For humans, I think we are very vulnerable right now. There's lots of humans on this earth, and we all depend on a few cereal belts, a few regions that produce most of our food. We depend on water. With changing climate, precipitation patterns will change. Temperature will, of course, change. Will these structures we have been putting into place over the last 20 years, will they still work? Will they be able to actually support all of us? I think that's highly questionable. On top of that, of course, we will see sea level rise. All these things will also happen if we stop emitting right now. But it will be maybe easier to deal with the consequences the sooner we stop. It might just be too late at some point very soon.
I think as humans, we've been able to do some amazing things with our own needs, like the crops we've been able to genetically modify to try to increase the amount of food resources that we have, to try to provide for these, huge increases in population in humans. But I think the question is, can we keep pace with the increases in carbon dioxide in the atmosphere and the changes to our climate? So we're seeing much greater extremes of climate and much greater extremes of very hot, dry events, particularly here in Australia. So it's a question of whether we're able to keep pace with those changes, even with such technologies as genetic modification.
So the Anthropocene is now a word that's very widely used. It's still not formally defined. There are people who are working on it. In fact, there are people here in our building, in our school, who are working on it. They've just had a paper about an actual marker for the start of a new geological era, the first sort of nuclear bomb spike that is recorded in tree rings, for example. But yes, I think there are many arguments that suggests we are entering a new geological era. So there's two things to think about here. One is, are we entering a new climate state? And I think most people would agree, definitely yes. But in terms of geology, so you have to think about what's preserved in the rock record, the geological record. And absolutely, there too, we are into there is actually a new rock forming now that's made up of solidified plastic. And that will not break down over time, but that is a new rock type that's been found offshore of Hawaii and various other places. And there are new chemical elements because of these nuclear explosions preserved in the sedimentary record of the sea. So geologically, yes. And because of the increase in the amount of rainfall, the amount of temperature, the rate of erosion is faster than we've had before. So there are thicker sequences of sediments in the deep sea that are accreting. So that is a recognizable change that we could see in the geological record. So aside from the pedantic niceties of saying geology, there are physical changes recorded by Earth in this sort of rock record that are suggesting we're into a whole new period.
Changes in our oceans, such as releasing toxins and plastics, can also have dire consequences for the diversity that we see in the ecosystems today.
Again, I'm not a biologist, but in my opinion, yes, I think we're in a period of mass extinctions. It's not the normal background extinction rate, the fact that every one of us has seen many species going extinct during our lifetimes. That really shouldn't be the case. So yes, I would say so.
So are we entering the sixth great extinction event? Many would say we're already in it. We haven't entered. We are not entering. We are in. If you look at the amount of species that have become extinct since really the dodo and the passenger pigeon in the States from the late 1800s, since then the rate of extinction of species is also one of these exponential curves.
I think that the evidence points to a sixth mass extinction. If we were able to time travel into the future and look back at the fossil evidence from today, we would see the last 10,000 years in a very short space of time. So we would see that the megafauna that were like the saber-toothed tigers and the giant bison across America, or in Australia we would see the megafauna like our marsupial lions and giant kangaroos and giant wombats would all become extinct in a very short space of time, as well as the increase that we see in extinction of species today. So I think that we have already entered this sixth mass extinction in the Anthropocene.
And, you know, the danger is that there are so many species that are uniquely primed for very specific purposes. When that purpose changes, say the size of a flower, the growth up a horizon of a mountain chain, where they live, you know, there are birds that only live within 400 feet of a particular mountain. They're being forced up the mountain, and eventually they're just going to have to go into the sky. Their habitats are disappearing as we speak because they're so fine-tuned for life. So as the habitats change, whether for good or bad, you know, climate change brings more growth in some areas, less growth, more dry in others, but that change means that species will go extinct.
A major issue that we as humans face today is species loss. And this is occurring through deforestation, building. This is happening all around the planet. And what's happening is that species ranges are becoming contracted, dissected, and they cannot move between one place to another. So this will affect the gene pool as well and genetic diversity, because there's really a minimum number of in a population to sustain that species through time and also in space.
Now, under natural geological Earth processes, nature would adapt and new species would arise to fill those gaps. But because the change is so fast now, nature cannot adapt at that speed. And that's the danger. We're left with a very few successful species that can adapt to change, and we're one of them. We can adapt. We live everywhere on the planet, so for us it's all fine. It's not fine, but we can adapt to that change. But there's so many species that can't, and they are disappearing now.
But my personal concern is really the change. Above all is the change in chemistry in the ocean, and also the change in water availability, and what is going to happen to our ecosystems, because our ecosystems are already under stress due to climate change. But on top of that, we add stress to overfishing, overhunting, habitat fragmentation, habitat loss. I think there's only that much that these ecosystems can take. And in a way, we are part of an ecosystem. We need an ecosystem to live ourselves. We need to eat, we need to drink.
One of the things about geology is about rocks, about processes that, you know, are preserved in the rock record, is that they compress time. So, you know, where the dinosaurs went extinct, that was probably over 1 million years, but we can see that as a layer about that thick. So if you think about all the change that's happening now, all the plastic and pollution that's going into the environment, as that goes into the deep sea and it gets buried and buried and buried, it gets compressed in these very thin layers. So that will have this enormous geochemical spike of all these manufactured components that will be preserved under a very thin horizon. So millions of years from now, if I was able to travel forward into the future and then come back and look and say, what has gone on here? Because it's so compressed, so much change is going on at that one specific interval. This is a massive catastrophe that would be recorded all around the globe. So you get these runaway effects. And so runaway effects, and we're already seeing it, right? So more than half or even 3/4 of the world's population live in low-lying areas at fertile river deltas at the coast of the oceans. All the big cities in the world are where there's a nice view over the ocean, right? So now, if the ocean rises 120 meters, OMG. The deltas, the fertile deltas, where all the rice is grown, where all the grain, all these things are grown, they disappear. And so as those oceans flood, and some people have suggested this can happen on the order of 100 years, more than half of our food source is gone. Fishery stocks are being depleted around the world. And those are primary food stocks. Primary food is the key. If we don't have the primary food stocks and fresh water, the basics of life, it's not about whether you got a mobile phone or a computer, it's about whether you've got food and water. And so if we don't have food and water, our population will totally crash. But less human pressure allows nature to expand. There's a lovely example in Chernobyl, where the nuclear disaster happened in Russia. The forests, the whole city was abandoned, and forests have come back. Wolves have come back for the first time in generations. There's a viable population with moose. There's a whole ecosystem and chain that is set up. So we know that nature can come back. It's allowing it the space and the time to be itself.
I think that the world we know today won't necessarily exist for too much longer if we keep increasing our carbon dioxide. But I think it's more the humans that we need to worry about. We're the ones who evolved in these much cooler times, much lower carbon dioxide in the atmosphere times, and it's whether we can help the species that we require and keep our diversity on Earth into the future and make our own species survive.
So yeah, we've got carbon dioxide rising, we're changing, we have to mitigate how we build, where we build, we're planning about the future, building back on higher ground, transporting water, using wave energy, all these kind of ideas about adapting to the new. If you then throw something on top of that adaptation, for many, including our species, that could be too much. Yellowstone going off would be a cataclysmic disaster. Yellowstone is known to have covered a third of the US in death-causing ash and gases, not to mention all the cloud effects and global changes in temperature.
Cut emissions now. As fast as possible. I think climate change is actually the biggest threat humanity has ever faced. And it's an interesting threat because it's something we have to do something all together. In terms of pollution, for example, if you have bad pollution in one country, then one country can decide that's not good for us and they change their policies and then it will be fixed. In this case, the whole human species has actually to cut emissions. The faster, the better.
The late Cretaceous, kingdom of the mighty dinosaurs. 100 million years ago, the ancient forests were full of life, not just dinosaurs, but insects, reptiles, amphibians, and tiny mammals that scurried through the undergrowth. The ecosystem of the tropical forest in a prehistoric greenhouse Earth is one of life and death, and sometimes a window into the distant past. In the ancient forests, like today, when a tree is damaged or attacked, it defends itself, secreting a viscous, sticky substance called resin. It protects the tree from infection or infestation. Over the millennia, the forest fell and began to form peat. Then with time, pressure, and heat, this organic material turns to coal. Trapped within the coal is the remnants of tree resin, which turns to copal, then fossilizes into amber. Sometimes things get caught in the resin, organic remains, such as plants of various kinds, even flowers, animals such as insects, spiders, frogs, and lizards. These are called bioinclusions. The amber preserves the creatures entombed within, giving paleontologists a window back in time. Sometimes we find inclusions in the amber that are unique, rare, and exciting. Many researchers around the globe consider amber to be the holy grail in paleontology. And there's a really good reason for saying that, in that specimens have exceptional preservation potential in amber compared to other types of rocks, that preserve fossil remains. So in fact, when we actually look at some of the amber remains, whether they be an animal, plant, or some type of microorganism, they actually look like they died yesterday. So they're in essence in a type of suspended animation over millennia or millions of years. So much so that you can actually see the most finest aspect of their morphologies preserved, from hairs, feathers, on a little dinosaur wing, to all kinds of insect remains and all of their body parts, perfectly preserved just like they died. So as a paleontologist, I need to get as much information as possible from a particular fossil. Say you go into a rock quarry and collect fossils. Most of those fossils will be from compression because they've been buried for over the millions of years. They've been essentially squashed into 2 dimensions. Amber is very different because those specimens are actually preserved in a 3D space. It's a paleontologist's dream to be able to study these fossils under the microscope and look at the finest details of their morphologies that have been preserved over the millions of years.
So the way we find amber in Australia, and especially in the Anglesey deposit, is a little bit different to how amber can be found around the world. It's very similar to how we find amber or how the Burmese amber is found. That's also found in a coal deposit. But the Baltic amber and the Dominican amber, which are quite well-known amber deposits, aren't found in that way. They're found by eroding that amber out over thousands of years from these deposits somewhere else, say around the Baltic Sea or around the Dominican Republic.
You get some types of resins which are quite clear and golden like this, and maybe a bit darker on this piece here, but some are a red color. You have some that are green. We have Australian amber, which is a very rare green type as well. You get a really rare blue type in Dominican Republic amber. So amber comes in different shapes, sizes, colors, all reflecting the different types of trees, and also what's called the diagenetic processes over the millions of years as well. So you can actually find amber in various ways, mostly from coal, other types of rock samples. You can actually find amber in petroleum wells, of all places. Most of the amber that was found originally in Australia was actually found just on beaches as float. So this was the Cape York Peninsula amber, which turns out not to be from Australia, but from someplace in Asia. And the reason for that is the amber floats in seawater because the density is quite low. But they can travel quite a long ways in seawater with the currents. So it's just surprising the diversity of ways that we can actually find amber in the geological archive.
So the coal comes from Anglesea. It's from the coal mine in Anglesea, and what happened was a bunch of researchers from Monash had found this very amber-rich coal, which we didn't expect to find, and it was very exciting. So they found a few pieces, they took them back to Monash. We've been working on them for a couple of years now, but then the coal mine was about to shut down, so we asked them to get the area where we knew the coal was. We just got diggers to take out a huge bunch of the coal from the side of the cliff, put it in a shipping container and take it here. Of course, this now means that we have a lot of coal.
The coal that we received from the closing down mine, we sort of, when we went there was a specific horizon where we found a lot of amber, but we just told the guys to get this much. So of all the coal in the shipping container, this much might be the area that has amber, and then within that there's even a smaller percentage that actually has amber in it, even smaller percentage that's large enough to see things, even smaller percentage that's clear enough to see anything in.
So when we first prepare the amber out, or first identify the amber, we'll see it in a block of coal like this, and it'll normally be a small orange or green blob in that coal. And the idea is to try and extract that without damaging it as much as possible. So we use hand tools, little dentistry tools and picks and probes, basically bits of metal with a point on the end, to scratch away at the coal that's surrounding the amber, to try and leave it on a little plinth, a little column that we can then crack off, and then we can take that amber somewhere else.
The issue is the amber is incredibly fragile, so trying to get it out using this method, generally you have to be very, very careful about it, which means that we only really focus on the big pieces of amber because they're the only ones worth getting out this way. Otherwise, we have other methods to get them out.
So in the Anglesea deposit, we get several different kinds of amber. We get oxidised amber, stuff that's been altered by water and the atmosphere as it's been close to the surface. And we also get very clear amber, and we get what we call dark amber. We have cloudy amber of both green and orange colour. So these ones here. Unfortunately, that's not very useful for us because it's cloudy, so we can't see into it and see if there's any inclusions. The dark amber is dark because it has a lot of things in it. It's mostly the reason. It has a lot of organic material in it. It has a lot of coal in it most of the time. And then there's the clear material, which is what we want to get out. We want to see clear material that is either green or orange that has inclusions in it. To date, we've found more inclusions in green amber than orange amber. Why that is, we don't really know. The difference in the amber is essentially a colour difference. But we do know that the green stuff has more stuff in it for some reason. We're not sure why. Maybe a tastier tree, maybe more sugar in it, maybe it was more sticky. We don't really know.
A lot of paleontology is a matter of vanishingly small probabilities, essentially. Because if you have an ancient forest, not all of the trees produce resin to begin with, and of those, not all of the resin that's produced is going to contact biology to be included. And then from there, not all forests turn into coal, and not all coal is preserved for us to see. Not all coal that is preserved is found by people or given to researchers or anything. So there's a lot to be explored, essentially.
And eventually we sort through that, get some more clear amber, and that will be amber a bit more like this, which we can start to see into and start to see if there's any inclusions in it. And if we're lucky, we might be able to get a nice big piece out.
Once we have a collection of amber from a piece of coal, we then look at it under a microscope. We paint it with water to clear it up, and we have a look through and see if there's any bioinclusions. So usually we get pretty small bioinclusions because we're working with very small fragments of amber, but there can be bigger pieces, and it is very exciting when we get those bigger pieces because that means we can have bigger bioinclusions.
it can be disheartening to work all the way through a large piece of coal and find absolutely nothing, because then you're just digging through dirt, essentially.
Sometimes we'll find something that's a discernible shape. It's angular, or it's a squiggle, or it's something that could be a mite or a nematode, something very interesting, in which case we sort of separate it out. If it's a big mass of materials, if it's a dark cloud and we can't make out any discernible shapes, then logically there's going to be something in there. We just can't see what it is. So we'll either take it to a high power microscope where we can look through it properly and possibly see any shapes that are coming out from that mass, or we can scan it, which is a very exciting thing to do. You use X-rays to create a 3D model of the amber, and then you can sort of pull apart the shapes that are inside the amber and actually look at what's going on there. Then we can have researchers looking through it and writing papers on the bioinclusions that we find.
We've got to clean all the excess coal off, wash it with a bit of water, but then to see into it, it's sort of like looking into, you know, a stormy ocean kind of thing, like the ripple fractures, and it's not polished, essentially, the amber, so it's difficult to look into without distortions. So to remove the distortions, temporarily we can put it in a fluid like cedarwood oil, which is literally the essential oil I get from the pharmacy. You have to be a bit careful with that. You can't leave it in for too long, and it can mess with the chemistry a bit, but it gives a really good preliminary look into the amber to see if there's any inclusions.
It surprises a lot of people to see when they actually look through a microscope and see the specimen. They can see the hairs on a fly. They can see the legs really perfectly. They can see every aspect of that creature that could be upwards of 100 million years plus old.
And then we look for other fossils within it. So we might look for insects, we might look for plant remains.
If you find something interesting, you can then embed it more permanently in resin, which is little things we make and then polish down.
To protect them, to harden them, to stop them from fragmenting even more, where we then polish that down to be able to see into the amber, see if there's any inclusions in it, and try and identify them from there. In fact, the first time I polished anything was a bit of a disaster. I had a small fly embedded in amber, which we wanted to polish some of the amber back on so that we could get very, very close to it and start to image the eyes. And fly eyes are very complex, so we wanted to try and understand the detail that was in there. And I polished, and I eventually ended up polishing half of the fly away, which was a bit of a mistake on my part. The other half of the fly was there and we could image that, but still it was not a very good result for my very first time trying to polish amber.
There we go. We find a few mites, we find nematodes, we find bits of moss. So these are the really small things that we're talking about, but still they're pretty exciting because this stuff is 40 to 42 million years old. And we don't have a lot of information paleontologically of this period in Gondwana. So any bit of information that we have about any ecology of the region is really, really exciting. We have found little bits of insects, ants. I found something the other day that might be fly legs, and they're very diagnostic of the species, those sorts of things, the antennas and the legs, which is what we find most commonly, but yeah. So my specialty is plants and geology and the interactions between the two things. And those are the things that I really enjoy doing. So this kind of work with amber, which is a plant resin, and finding plants in the plant resin is really exciting. So, yeah.
So amber miners they've been mining amber, which is called bermite there, for various reasons. But the bermite's been mined in northern Myanmar, believe it or not, for over 2,000 years. And this started during the Chinese Han Dynasty. And so over the 2 millennia, miners have been, looking for amber there, which is focused in a fairly small little area of that country. And scientific significance really didn't come to the fore until the last several decades, when we started learning that this actually represents a terrestrial ecosystem that's about 99 million years old. So it gives us a glimpse into that tropical environment. So we're talking about a time when this part of Myanmar was really close to the equator. So we're looking at what's called a Cretaceous greenhouse Earth, 99 to 100 million years ago. And at that time, heat was being distributed more evenly around the poles, so all the way from the equator, all the way to the poles. And it was also a time of increased resin production of trees. So there are various trees that actually produce resin. Okay, and this particular tree is related to the Cupressaceae, which is one of the cypress families. Okay, and these particular trees produce a lot of resin. And once in a while, something absolutely extraordinary will be found. We've actually found a dinosaur wing recently in the bermite. So a student is actually studying that at the moment. It's quite important because we can actually see the individual feathers of this wing as well as tissue, bones. So we have a lot of work ahead of us to actually try to reconstruct what this wing represents. Is it a non-avian dinosaur or an avian dinosaur? So avian dinosaurs represents early birds, something like that, or is it something else? Is it a type of early theropod dinosaur? So hopefully by studying the wing itself and also the feathers, that we'll be able to find out exactly, what that wing belonged to in terms of whether it was an avian or non-avian dinosaur.
So the amber is Cretaceous bermite from Myanmar. It's roughly 99 million years old. And within this particular piece that I've been studying is a dinosaur wingtip. And so within that you can find feathers, and it can provide a lot of insight into feather morphology and the evolutionary development of feathers over time. Associated with the wingtip is arthropod inclusions, and those can provide us a little bit of insight into ecological interactions. Many theropod dinosaurs, not necessarily just the avians, were believed to have feathers. However, due to the size of the specimen that we're looking at, it's most likely a juvenile. However, small avian dinosaurs have existed within the fossil record. So the difference between feathers within this piece and modern feathers are they are slightly less complicated. The evolutionary history of feathers has seen increasing complexity throughout geological time. And these feathers, whilst they're very similar to those of modern birds, they're not quite there. They lack some of the distinguishing features that would allow us to determine the fact that this is a modern bird as opposed to something that is more primitive. So our next steps in analysing this piece is to be able to try and isolate the different types of feathers that we're finding with it. A single specimen will have more than one type of feather morphology, and so to be able to identify each of those, we can get a better understanding of where this species would fit into the evolutionary history of modern feathers. Through being able to understand past environments, such as that of the 99 million year old Burmese forests, it can give us insight in how modern environments would react to things like climate change or other disruptions of evolution of developmental processes. If we can understand how these species and organisms interacted with each other and evolved back there, then it's possible for us to apply that knowledge to current ecology. They have found specimens with quite vibrant coloration, so the coloration patterns that we see in modern birds wasn't necessarily unique to present time. Even 99 million years ago, in the age in which these feathers were first developing, they still had vibrant colours and creative patterns. However, these are rarely preserved within the fossil record, but there have definitely been instances in which we've been able to observe these. But it could definitely mean that a lot of other dinosaurs had vibrant colours that we haven't yet observed in the fossil record, but it could have occurred. So through using the synchrotron scanning that we're hoping to complete soon, it would be possible to look at the bone structure and the bones themselves. Through that, we might be able to identify the species, but also be able to determine the species' age through looking at bone growth signals. And if we can do that, then it's going to give us a lot more insight into what this specimen actually is, whether it's a juvenile or if it's mature, whether it's an already identified species, or if it's something that could be completely new.
Paleontology has advanced so much in terms of imaging that there are several techniques that we can actually use to study, okay? And we can actually use various microscopes. We have Leica microscopes we can use, such as the 205C. There's also the BK imaging system that we have here at Monash University. If we want to look internally and externally, we have to use other techniques, such as micro-CT scanning as well, and this is a type of tomography that we can use, and also advanced synchrotron radiation as well. So, in fact, we can actually look at this, and we have done so. At the Australian synchrotron, and we did that using what's called the IMBL. This is the imaging medical beam line there. So that has given us information about the internal aspects as well, and also the micro-CT scanning.
With this method, I think we just need higher resolution. So the best way is to cut the sample and to do thin sections. So to show you that's looking at the data at 75% full scale. Okay. So this is now the data in full resolution.
People often ask when I'm holding a fossil like this that maybe has some remains preserved, such as a little bit of a dinosaur or something like that in amber, or a feather, can you get DNA out of that? And the answer is no, but we can actually look at the elemental compounds of this too to see if there's anything preserved. And so some ways of doing that are Raman spectroscopy, FTIR analyses as well, and we've actually found out that there's concentrations of iron, so these would be heme compounds from blood that are still preserved. So you can still get some elemental composition, from this, and so this is advanced chemical techniques that we can actually use.
Raman spectroscopy is a technique to study molecular bonds in our sample. It's based on the interaction of light with matter from the sample. It's more specifically based on inelastic scattering of the light. So the concept is that we flash light on our sample and that light gets scattered, either in an elastic or inelastic way. Actually both. The elastic way means that the scattered energy is the same as the energy of the incident beam. Whereas the inelastic scattering, which is Raman scattering, means the energy of the scattered radiation is equal to the energy of the incident beam plus or minus the energy of the bonds present in our sample. So in other words, through this technique, we can determine what sort of bonds we have in our sample. So what sort of molecules do we have in our sample? Piezo states, but piezo states allow 300 nanometers.
I like seeing a spike on a graph. Yes.
Well, I'd love to see an
Instead of a
actual band like that, but...
Yeah. There's still something going on. That's really interesting. In terms of fakes and amber, yes, I've actually looked at lots of fakes just to get a better feel for it. And there's several tests that you can do as well to discern whether the piece you have is actually an actual real piece of amber or whether it's something that somebody's faked in some way. Because there are specimens out there, and you see them all the time. You go to a market, you'll see a piece that has a big scorpion in it. It looks like it's it's a fake, And how do we test that? And there's various techniques that we can do. We can actually look at the specimens that are associated with a piece like that as well. If there's nothing else in it, usually amber almost always has a lot of organic debris in that too. So that's also an alarm bell that should ring off. If you see a perfect piece, has nothing else in it at all, no other inclusions of any kind, froth or little bubbles, nothing like that, then you could think, oh well, I better check this. So you can actually do what's also called an ultraviolet test, UV test. So real amber fluoresces a brilliant blue, which is quite extraordinary when you look at it. And it's so good, though, that you can actually see the various flow patterns as well, which also tells you that a piece is real or not. When you actually heat it as well, amber starts to melt at around 200 to 250 degrees centigrade as well. In fact, some amber today is used in varnishes and that kind of thing. The black residue is used in varnishes. And it's also used for medicinal purposes as well, in natural medicines and therapies. So you can look at that as well. It actually floats in seawater. So if it just sinks straight away in seawater, you might want to consider that too. And a lot of amber today and little resins are reconstituted, so they've been reheated as well. But what's really interesting that you can see in terms of the inclusions is that sometimes you'll find the finest, what's called stellate hairs or trichomes from plants, which is so delicate that you cannot, if you reheated it, they would be gone. So you can just tell by the association of organic remains. Sometimes you'll say, oh, well, there's a fossil that's only found in the Cretaceous period with dinosaur wing. You say, okay, well, that, these have been described already. So there are lots and lots of different techniques that we can use. And you really have to look at all of them. But usually a paleontologist who has lots of experience can look at it straight away and say, oh, okay, this is not right, or sure, this looks right to me. Let's do these tests and confirm it. One of the other extraordinary specimens that we found just recently is a section of a little reptile, probably a gecko called Cretaceous gecko. And this particular gecko is so well preserved that the actual skin is there and preserved. We can actually see the little feet as well, but the skin reveals a really complex pattern on it. And you cannot get anything like that preserved in the fossil record unless you look at amber, really, to have that type of preservation in terms of the finest details of the skin pattern Okay, and it's quite extraordinary. We've also found pieces of Burmite that have snails in them as well. Terrestrial snails are quite rare in the fossil record. We also have invertebrates that we're trying to work out what they are exactly. So paleontologists don't always know exactly what we're dealing with. And sometimes the fossils, because they're 100 million years old, they're groups that became extinct during the Cretaceous period, just before the mass extinction. And they're very different from what's living today. As paleontologists, again, we really want to be able to reconstruct those ancient ecosystems the best we can. We've actually found that so many different types of animals and plants are being found in the Burmite, or the amber of Myanmar, that it's really giving us major clues as to what kinds of organisms lived in this ancient tropical forest.
So, the way we date is to do a process called relative dating. So we have to look at the surrounding coal, and then where the surrounding coal is in its stratigraphic sequence, where it sits within the Earth, basically. And then we look for other fossils within it. So we might look for insects, we might look for plant remains. But most importantly, we'll look for pollen.
Pollen is incredibly diagnostic of the tree species. So you can look at that pollen and immediately tell, yes, that's the tree that produced that pollen. If we know what period of time that tree lived in, then we can use that pollen to say, this amber was most likely produced from this year to this year. And we have found things in the amber that resemble pollen.
The advantage of that is that pollen changes rather rapidly in geologic time. You have species changes reasonably quickly in geologic time, whereas for things like trees and leaves, the morphological changes of trees and leaves are slower.
But if we can use that to narrow down, instead of saying 40 to 42 million years old, we could maybe narrow it down to 40 to 41 million years old. It's still a very broad range of time, but it's still quite diagnostic.
Closer to home here in Australia, we've made some extraordinary discoveries in the Anglesey coal measures. Okay, this was the Alcoa mine, and it really blows our minds as paleontologists because we're actually getting behaviors preserved as well. So we have one instance now, we've just found it just weeks ago, where we have 2 flies that are preserved. So when we started looking at this specimen, we could see one specimen. We thought it was a fly, but we weren't sure. And my eye could just capture something just a little bit deeper inside. So we had to polish it up really well. And lo and behold, we saw one little fly kind of attached to it. And then when we actually rotated it, we could see, wow, they're actually mating. So we actually captured in the resin, which is 42 to 40 million years old. So we're talking about quite ancient times here in Australia. When Australia was still attached to Antarctica, we actually have now a specimen of mating of these flies, which are part of a group called the long-legged flies in the family Dolichopotidae. So it's a really important, and as far as we know, it's the only fossil ever found in Australia that actually shows sexual copulation happening or mating, so all of our students are creating little captions for newspaper articles and that kind of thing about what they're called, what we could call this, such as doing it Gondwana style or something like that. So there's been a concerted effort in the last few decades to learn more about this Cretaceous ecosystem in Myanmar from the amber, because we do know it's a terrestrial environment, it was tropical. So as paleontologists, we really want to learn more and more about what animals or what the organisms were, what made up this ecosystem in this really interesting part of the world during this hothouse environment. So it's much hotter than today. So CO2 levels were a lot higher, temperatures were a lot higher overall. So it's very different from today in many respects.
It's not likely to impact things that we look at now on modern species extinction, but part of jobs of a biologist and a scientist is to understand where we came from and how we've evolved over time and what our relatives were like.
One of the primary goals of paleontologists is to not only reconstruct the ancient ecosystems through time, which is a really tall order because rocks imperfectly preserve fossil remains. So much so that we think that we only know about a fraction of 1% of all the organisms that have lived through geologic time. So we don't really know that much, but we have to really focus on those deposits that capture all these ancient remains as much as we can in terms of diversity. So we're very fortunate that we have amber, to look at terrestrial environments. As paleontologists, we really want to build a picture through time of the ancient organisms that lived, that tells us more about evolution. As an example of this, in Australia, this is a primary example. Where did ants come from? You ask anybody, so entomologists studying ants, where did they come from? And nobody would know because we've never had one fossil of an ant preserved in Australia. Lo and behold, in the Anglesey coal measures, we have lots of ants preserved. And so they're giving us an insight into ant evolution for the first time, which tells us that groups, and this is the genus Monomorium, Monomorium has lived in Australia and been an important part of the terrestrial ecosystems in Australia for at least 40 million years, when Australia and Antarctica were still attached. But before that, if you didn't have the amber, how are you going to get ants preserved?
It's partly the fascination that we can really see the actual part of the animal that existed 100 million years ago. That's an astounding thing and one of the great privileges of being a scientist and looking at things that nobody's ever seen before. People have been looking for this type of thing for a long time, and it's a great excitement to be able to really see these unique images back into the history of mammals.
The question is no longer if, but when. Looking for life beyond Earth has been a human obsession for centuries. Science is overtaking those visions. We keep looking, and we're getting better at it. Science and fiction are about to meet in the middle when, not if, we come across life beyond Earth. It appears the fundamental assets to make life are distributed throughout the solar system, a function of the evolution of planets. What at first glance appears a simple question, where can life be, rapidly spirals into a complex conundrum. The complexity of DNA here on Earth, and what other environments could facilitate such growth in complexity. Can biological life even get started in the harsh conditions of the solar system? Until concrete evidence is available, the question is polarizing.
I can't say for sure because we've only got the one example of life on Earth to work with so far, but all the ingredients are out there. Solar systems make everything you need for life, insofar as we know. So it could be that matter naturally organizes itself into life.
My answer to the question of whether there's life out there in the universe is, I'm afraid, I don't know. The great thing about being a scientist and not a politician is that I'm not required to have an opinion on anything. I'm only required to be able to tell you what the facts tell us. And what the evidence is that we don't know. We don't know how life on Earth got started in detail. We don't know how long it took. We don't know what the preconditions were. And so life could be incredibly common, because there are lots of planets out there, or it could be an incredibly rare event that only happens, on 1 in a billion planets in a galaxy.
You want to have fluids available. So water, insofar as we know, is necessary. It's necessary for biogeochemistry on Earth. So you would expect that anywhere where you have liquid water or liquid organics would be good places to look for life.
Another question for scientists. The environment that hosts life now may not be the originating location for that life.
Life now occupies almost every imaginable niche. Most rainstorms are seeded on bacteria that float around in the water vapor, and then they start to nucleate water droplets and down they come. So, life is just everywhere. And it's in Antarctic ice caps and in snow patches. And so it's everywhere at the moment. And it can survive for unbelievably long periods under harsh conditions. But are those the conditions you need to make life? Those are kind of two steps we've got to almost detach our minds from in two different kind of views. So that whole idea about, where do you start life? Because the most primitive organism is already an unbelievably complex piece of machinery. It's got a membrane that isolates an interior component that's different chemistry from the outside. It's got a mechanism for mobility. It's got this incredibly complex molecule inside. So those are almost like different pieces of a puzzle put together into something that works and can then self-replicate and such. So, even before you get to that stage, you have this immense series of events that we can't even really begin to understand yet. We're starting to, but how do you get to that stage? So you almost have to detach yourself from life, where can it live now, to the building blocks of life.
Life as we know it is a complex mechanism, capable of self-replication and great diversity. But what actually is it? How do you go from a puddle of organic chemical broth, exposed to some form of energy, and turn into this?
Meteorites do have potential for astrobiological exploration, and they're actually pretty delicious for microorganisms. They have a lot of available, phosphorus, which is essential for all life as we know it, sulfur, carbon, organic matter. It's not a bad place to live, and we know a lot about meteorites. They're the best studied rocks in the solar system. So there's a very controversial meteorite, the Allen Hills meteorite. In the mid-90s, there were some studies released that put forward the idea that they might have contained nanobacteria from Mars. So the Allen Hills meteorite is a Martian meteorite, so part of the crust, the surface rocks on Mars. And it would have been ejected from that surface and fallen to Earth at some point in the past. And there were morphological features that looked like microfossils. However, the results are still ambiguous. It's really difficult to determine whether a textural feature like a microfossil is true evidence of a biological process, of the presence of cells. So typically we want to use microfossils, so textural evidence, an imprint of the cells or life that were in a meteorite or in a rock from another planet or moon. So we want to look for fossils and chemical evidence in terms of organics and inorganic chemistry.
Recent discoveries of fossilized microbes called stromatolites in Greenland are helping pinpoint the earliest evolution of life. The time window is narrowing, allowing for more accurate searches elsewhere in the solar system.
Yeah, well, it's an extraordinary discovery in really two different ways. One is that these stromatolites are preserved at all in rocks that are 3.7 billion years old. We're just talking incredibly ancient periods of time. And the exciting thing is, and we put this in the title of the paper, that we talk about a rapid emergence of life. So these rocks in Greenland are actually almost the oldest preserved rocks in the world of anything. And they're preserved in the immediate aftermath of what's known as the late heavy meteorite bombardment, which we know about from studies on the moon was an intensive period of large bolides coming in and really impacting the Earth with incredible energy. In fact, enough energy that the oceans would have vaporized and had to recondense again, up till the period about 3.9, 3.8 billion years ago. So the thing that it's starting to point to is that, if life got started really early on Earth, and maybe it did, maybe back to 4.2 billion years ago when we know there were liquid oceans, it's hard to imagine it surviving through those incredibly energetic impact events until about 3.9, 3.8, and then we've got evidence of stromatolites at 3.7. So it's all about how long do you need to make life? That chemical soup, that energy to generate complexity, we always thought it took 500 million or 1 billion years, but these discoveries are just shortening that time frame down to 100 million years, which sounds like a lot to you and me, but actually on geological timescales, that's very short. And so it's really exciting in terms of thinking about what does that mean for generating life on other planets that don't have the long history of geology that Earth does. We're still an active planet, but Mars, other planets have died because they're smaller. But then the question is, could they have formed life? Well, this foreshortened period suggests that, yeah, maybe they could. And that expands our envelope for thinking about where to search for life in the solar system, in the universe, really everywhere. At the moment, a developing paradigm shift in the community about where did life get started on the planet. So at the moment, it's known, or it's been theorized, that life started in the deep oceans by these hot vents that extrude mineralized water onto the sea floor, 400 degrees temperature. Thousands of meters below the ocean's surface, no sunlight, just chemical energy. And that's been a really evocative model for a long time. But now, people are starting to see that there are problems with that model. And it's not about life living at those vents. We know that's the case. We can see it with our rovers. When we go down, we see these big tube worms and crabs and everything. But before you get life, you have to make organic molecules become more complex. So organic molecules are simple, they're everywhere, they come in from meteorites and comets and dust falling in and stuff. But to make them complicated, to make them long chain, you've got to stick those bits together. And the funny thing is that sticking those bits together requires not just wetting, but drying conditions. Each of those reactions that makes an organic molecule longer requires a water molecule to be kicked out. So the community is starting to realize that actually you can't make life in the oceans. It's actually too wet. So we're now, and with a group of us, looking at hot springs, because hot springs on the surface of the Earth have all the conditions of the deep sea smokers. They're not as hot, so that's actually better. And they have the capacity for wetting and drying cycles on the edge of hot springs pools that have geysers. They erupt and they expand and they detract. And so you get these wetting, drying cycles. That provides the power and the energy for making complex organic molecules. And their chemistry is very complicated. Each hot spring is different. One's pH 2, one's pH 7, one's pH 11. They've got different nutrients, different chemicals. And you mix and match all those things together, and all of a sudden you've got complexity that could make life in something like 10 million years. So this is a new model that we've just published in Scientific American. Very exciting. And it's applicable to Mars. Because it looks like from the history of the geology of Mars that actually it never had oceans. But it had volcanoes and it had hot springs. So if our ideas about the origin of life are changing from the deep oceans, where we'd say, why would you go to Mars? They never had deep oceans, so life wouldn't start there. To hot springs, all of a sudden Mars are going, very exciting.
The next obvious target for scientists is our age-old agent provocateur, Mars, the closest in time and space to our Earth, and the best first chance of evidence of non-terrestrial life.
Absolutely. We're looking at exactly the same window of time as the discoveries from Greenland through to our well-known work in the Pilbara in Western Australia, where there's the most convincing evidence of life. The whole community's satisfied about it. But that window, 3.8 to 3.5, is exactly the time in the history of Mars that we know it had warm and wet conditions, or at least wet conditions with abundant flowing water. And so that's exactly the window that we're looking at. And that's why these areas are so important as analogs, because they really are, a window back onto this incredibly deep time period, and at the same time on Mars.
The next Mars rover mission, Rover 2020, is fast approaching.
We're literally on the advisory team for one of the landing sites for the Mars 2020. We've gone over the past 2 years to the landing site workshops where they're whittling down the numbers, and at the moment they're top 3 sites candidate for the Mars 2020 mission, and ours is still one of them, and that's to go and look at what appear to be, from all the evidence we have, hot spring deposits. These silica-rich deposits from extruding hot water that's coming out of the ground and flowing over the landscape. And we're so excited about that because the work that we've done in the Pilbara has shown that at 3.5 billion years ago, the same age as the crust on Mars, this ancient life on Earth was thriving in active hot springs with geysers depositing opaline silica. And they found from one of the previous rover studies on Mars, the Spirit rover, found opaline silica deposits. And they've got textures. I mean, this is totally mind-blowing. They've got textures like these little fingers coming out of these silica things. So it's not just boring layered rock. These have vertical structures, finger-like structures, and they found identical structures in hot springs active today in these very high desert areas in Chile, the most Mars-like conditions you could ask for. Bang, we've got the same structures, opaline silica, these finger-like structures, and on Earth, they're made by microbes. So we're saying, go to those known hot spring deposits on Mars.
I really hope that we do find fossilized microorganisms on Mars. That would be a triumph for science and for humanity. I'm not holding my breath, though. It could be a long journey to try to find a record there, but it's probably our best hope in the solar system.
Beyond Mars, the next outposts in our solar system to be potential habitats for life are the ice moons of Jupiter and Saturn.
Europa, everybody gets very excited about because we believe that it has got quite a thick ice crust, or thin or thick. Again, we're not entirely sure how much, but there's a global ocean underneath that ice, and that should boundary straight onto a rock mantle, a rock inner core. So at that interface, you've got rock and water, quite warm, like probably more than room temperature. So you've got potential for that water to pluck out minerals, nutrients, and then of course that whole ocean is shielded from the intense radiation of Jupiter. So it's a rather snug little place to be.
But this gets back to the origin of life, right? So we have life occupying these chemical hot springs down deep in the oceans. And they're some of the most primitive organisms, no doubt. But it gets back to that question of how do you make something that's as complex of life from very simple building blocks? If you can't do it in the oceans, then I would say you're wasting your time going to Europa and Enceladus, because those deep oceans would never have the wetting drying cycles. So they probably and very likely have the kind of elements we see in the deep oceans on Earth. They may have hot smokers, they may have mineralized water-rock interactions, but from our group's perspective, if you never had an exposed land surface, you probably never got life. And so without that, we'd really question whether it's worth going.
Perhaps meteors punch through the ice crust to deliver the additional organic chemistry required.
Potentially, yes. I've seen that there's a big change in the craters. So there are craters on the surface of Europa. Let's talk here. The surface of Europa is very young geologically. It's at most 100 million years old, which is why a lot of people get excited about the potential of activity. Craters up to about 30 kilometers are pretty normal. They compare normal for an icy satellite. They compare quite well with the similar sized craters adjusted for gravity on Ganymede and on Callisto. Now, once you get above 30 kilometers, they change very dramatically in morphology. You don't get the sort of big crater, you don't get such the crater shape, you get a sort of ring-like structure. Now, again, the modelling of that is not complete, but you could imagine that that's happened because something's actually punched all the way through, and then water is sort of squidged through, and it would maybe form that. There's a big debate as to how thick or thin the Europa crust is, but I believe that from the cratering record people see, it points to it more being in the 20 kilometres range. That's good because it would definitely protect anybody down there. That's bad because it's very difficult for us to get down there and actually go and find them. So we'll still see.
The next possible habitat is the outer reaches of the solar system, a newly visited world showing a complex environment with the potential to harbour microscopic life.
One of the really fascinating things is some of the surface coloration you can see in these images actually shows that there are these compounds called tholins, which are a combination of elements, but they're related to prebiotic molecules, so they're kind of relevant to prebiotic chemistry. And I think the fact that they have been able to form on planetary surfaces very far out in the solar system at very cold temperatures really has implications for a lot of places. I mean, if you can imagine for star systems outside our own, where the star may be dim and the planets are quite far away, it's interesting to know that there are molecules that could be involved in supplying biotic material to processes that may one day lead to life or be involved in life or something like that. They're actually forming way out in the solar system where no one really expected.
Now, the exciting thing about Pluto is what we didn't know until we got closer up is that it's got a complex history. We can see different domains, and that means there was activity there. And if there's activity, like geological activity and organic molecules and a surface, then there's interesting stuff going on. So actually, that looks like an interesting environment. The missing part of that equation in terms of thinking about complex life is the sun is so unbelievably faint at Pluto that you'd never have probably the possibility for photosynthesis, which is what allows oxygen to rise and allows for complex like us and elephants to be around. That's a whole nother step away. So we wouldn't predict, a complex advanced civilization on Pluto, but maybe microbes.
Before we found exoplanets, before we found planets around other stars in 1995, everybody expected that planet formation elsewhere would produce systems that look just like our solar system. And for about 20 years, what we consistently found was thousands of planetary systems that look nothing like our solar system. We've got gas giant planets that orbit inside the orbit of Mercury. You've got gas giant planets that orbit where Venus, Earth and Mars are. You've got planets in highly eccentric orbits, highly non-circular orbits. Almost all the orbits in our solar system are really quite circular. Most exoplanets, most planets around other stars don't have those nice circular orbits. We find system architectures that are very, very different from our own, which suggests that maybe the structure of our own solar system is not the norm. Maybe it's unusual for reasons that we still don't understand. Planetary system, even just the Earth, is an incredibly complex system. And we are yet to understand the sort of multiplicity of what other planetary systems look like. The other thing to bear in mind is that saying that other planetary systems should look like our own solar system is an incredibly risky assumption to make.
The variety of planets we are finding is indeed fascinating, from hot gas giants of various sizes to terrestrials varying in dimension from moon size up to 2 or 3 times the size of Earth.
So, finding planets is hard. It's really hard. Finding life is that much harder still. At the moment, the prime focus of most of the people who are looking for planets around other stars is not so much to look for signatures of life, but look for signatures of habitability. That is, an environment that is similar to what we see here on the Earth. So a roughly Earth-sized planet at roughly the same sort of separation from its host star, modulo the brightness of the star. And then potentially saying, well, can we see the properties of the atmosphere? Can we see whether it's got water in it? Can we see whether it's dominated by thick clouds of sulfuric acid like Venus, in which case it's probably not going to be habitable, or has it got a relatively thin atmosphere like the Earth? The Earth's atmosphere is actually quite tenuous compared to the atmospheres of lots of planets. So it's sort of finding out those properties. That's even harder. The next step is what are the signatures of life that you look for? Do you look for methane emissions? Do you look for the signatures of molecular oxygen? So when the Earth first formed, there was no molecular oxygen in the atmosphere. Oxygen is a byproduct largely of life, of the cyanobacteria that formed in the oceans earlier on. So those are the sorts of signatures that you could try to look for. A lot of that is sort of guesswork because we don't really know how life on our own Earth got started. Trying to guess what life on another planet would look like, we're sort of limited to looking for something just like ourselves. There's no guarantee that the only pathway for life is to look just like us.
So what we expect to find on other planets, in some ways we don't know that they'd be different in the broad view, because organisms still have to be able to do the same things. They have to be able to get energy, they have to be able to get nutrients, convert all those to useful products, and they have to be able to reproduce. So organisms are always going to have these characteristics, and we are confident that in order for animals or any organisms to become more successful, there has to be some sort of natural selection. So the way natural selection works is that you have variation amongst individuals. There are many more individuals that are made that can survive in the environment. Those that are better able to do their job have more kids, and we start moving along that trajectory of accumulating adaptations, things that they're able to do better than others outside. So these basic processes are going to be what drives the change in life over time. Well, there's a lot of basic physical conditions that are going to be common throughout planets and the life forms that evolve on them. And so being able to sense distance, I guess, is one of those things. Could you get better depth perception with more than two eyes? It's hard for us to tell. Well, so many animals have many more than 2 or 3 eyes, and it depends really what you want your eyes for. So there are lots of organisms that have very simple eyes. Say a jellyfish has light-sensing organs that go all the way around its body, and these are able to help it move towards or away from light. But if you want to be able to actually form images more than just light sensing, these are structures that have to be evolved, and they take up more space. They presumably also take some degree of brain power to be able to process that image and make them useful. So if you had only 2 eyes and they could basically see 180 degrees or more than that, is that ever going to be, are you ever going to need more than that? But we always know that the further apart you put the eyes, the better your depth of perception will be. I guess one of the things that might be advantageous of having multiple eyes is that you could have different eyes that do different things. So there are some fish that spend most of the time underwater, and so to make it so that eyes work well underwater, you make your optics, the lenses, act well underwater. But then if the fish wants to look above the water, the optics are all different, so they can evolve separate eyes or separate parts of eyes that are designed for looking through air rather than through water. So having multiple eyes that do different things would be an advantage.
How about mobility? How many legs are best?
2 legs is pretty unusual. So 2 legs is not an advantage for most of the situations because they're quite unstable. And so it takes us more effort to be able to stand on 2 legs. We're more unstable, more likely to be knocked over. If we run on 2 legs, we're more likely to trip and fall than an animal with 4 legs, where you can have additional points of contact with the ground, and running fast is actually easier with 4 legs compared to 2, with a galloping gait rather than a running gait. But when we look throughout the animal kingdom, we have a lot of different diversity in the number of legs, if we're talking terrestrial animals. And we know that more primitive arthropods like millipedes and centipedes have dozens of legs on their body, but arguably more successful groups like insects have said 6 is enough for me, and so they have sort of set their body plan to say I only need 6 legs. I can do a lot, I can change those to do different jobs, but with those 6 legs, I can become the most diverse group of animals that we've ever known. There are other variations on that. You get spiders that have 8, you have crab-like animals that have 10. So part of the decision of how many legs you have is how adaptable can you make any of those legs. If you do have lots of sets of legs, that's going to limit some things that you can do. If you're always going to have a long, thin body with lots of similar legs, you won't necessarily be able to make big, strong claws for doing particular jobs. You won't be able to change your back half of your body to fit all of your digestive organs or your reproductive organs, which is what insects do. They've taken all their legs off their abdomen, then they have this large structure that it's not filled in with all the muscles and joints of legs. They can now put a lot of their organs in those. So in many ways, getting rid of some legs is useful. Well, we know that looking at animals now, we're looking at a tiny fraction of the total diversity of life that has ever existed on Earth. So we have a very biased view in what we think is possible. But looking back in the fossil record, we can see that animals that in some ways defy description have existed. We don't know exactly how they lived, and we imagine that many of these were sort of evolutionary dead ends. They tried something out. It was successful for a while, but something outcompeted them, something ate them to extinction, and extinction events themselves will have taken portions of that diversity away.
One thing we do know about evolution is that, there's a certain number of available habitats. And when they get filled up, life doesn't actually need to evolve very much because it fills those habitats. So, the dinosaurs and that community was around for 150 million years. They were pretty successful. They filled up essentially all the different niche space with the plants and everything else and stuff, and the pterodactyls in the sky. And it took a meteorite impact to break that effective filling of the niches.
After that time of around 66 million years ago, when this major extinction event happened, there has been phases of cooling of the Earth, and perhaps that would have greatly affected dinosaurs in different ways from the extinction event. And that's one of the things that mammals have been able to diversify into is this change to a cooling Earth that increased body size and furredness has enabled them to fill those roles.
And so these extinction events, these impacts or giant volcanic events that change the atmosphere and stuff, they're almost like wiping the slate clean and you can start over again. And so then life adapts very quickly during those change periods and fills that niche space again, but it does so in a different form. And that's where these evolutionary steps are able to develop. And at each step, you could argue that there's increased complexity, but one of the things we're finding out is that we're not alone in being intelligent, right? Dolphins are very intelligent. They're the top predator in their niche space. There's all this incredibly complex interactions between predator-prey and, building up chemical arsenals. And it's just incredible what happens on a daily basis. And so you could argue that development of intelligence is an inevitable consequence of increasing complexity and development through time, whether it's in the form of a human or a porpoise or a dragonfly or something, Once they have to figure out ways to solve problems to be competitive and develop the right tools, then there's that possibility of developing great complexity. Because you and I, and really all life on Earth, is just a matter of organizational principles. It's really just complexity, right? So we're able somehow to stand on 2 legs, whereas most walk around on 4, but that's an adaptation to environment with this changed niche space. So you could argue that if you let that experiment run again and again and for longer and longer, that you would probably end up with something that has intellectual capability in terms of problem solving. And we know that now. We know many animals, even spiders, use tools. So, we're finding we're less and less unique, but the level of complexity and adaptability is certainly, at a very high level in humans. And time is a great friend, Time gives you that ability to complexify. But the extinctions, maybe they were a really critical marker in terms of allowing this form of complexity to develop.
Other considerations when it comes to exoplanet environments have to include differing gravity, atmospheric density, and planetary spin around the star.
Within a reasonable degree of changing gravity, I don't think that would have a big difference. Only with a massive change in gravity would I think things were different. But if, say, you decrease the gravity a lot, that would make flight easier. So maybe you'd find many more animals that are flying or gliding than we do on Earth. If you made gravity stronger, you'd probably decrease the frequency of flight because it takes more energy to be able to overcome that force of gravity.
What about size? Would differing gravity create larger creatures?
Depends in part if you live in the air or underwater, because when you live underwater, you are supported a lot more. So the largest animals that we've ever known live in the sea. They're the blue whales, and so their skeleton and their limbs don't have to be able to hold their entire mass. For living on land, there's some that suspect that the maximum size of vertebrates that we've seen, which include the dinosaurs and some mammals are still relatively big according to that. We think that their body size was not limited by the mechanics, it was by being able to get enough food to feed a very large animal. So being able to find a high enough energy food source and being able to move over the environment to get that seems to have been one of the major factors that limited their maximum size. So we think that they could probably get bigger, but they'd have to be able to feed themselves and have a big enough population to sustain themselves over a long time. If you had a very fast spinning planet where you're changing from night to day very frequently, you would get less specialization in animals that do stuff at night and animals that do stuff during the day. I would expect they would just be adapted to exist throughout that whole night-day cycle. And then if you go the opposite way, where you have a planet like Mercury where the same face always faces the sun, it's possible that it's way too hot on the side that faces the sun and way too cold on the other. And we might imagine that there's some sort of lovely habitable zone but in that small gap between them where all life happens. And they then only have a single night-day combination for the whole of their life.
In 1961, astronomer and astrophysicist Frank Drake came up with an equation to determine the number of intelligent extraterrestrial civilizations that might exist in the Milky Way at any one time. Several factors of the equation are highly conjectural, leaving a great deal of uncertainty about the answer.
So the Drake equation essentially combines together a bunch of different uncertainties. It breaks the problem of, do we think that there's intelligent life out there in the universe that could talk to us, down into a series of terms. So there's a term for the rate at which stars form in our galaxy, which we actually know reasonably well. Then there's a term for the rate at which stars have habitable planets orbiting around them, which we're starting to get a handle on. It's probably, somewhere between 1 and 100% of stars. And then there's a term for the time it takes life to evolve, which frankly, we've got almost no idea about what the mean time is for that happen. We think on our on Earth, it took somewhere between 100 and 500 million years for life to first get started. And then there's the rate at which intelligent life forms. And we have absolutely no idea. We have absolutely no idea how you go from the timescale to go from bacterial life or pre-bacterial life to multicellular life, to eukaryotes, which are multiple cells all living together. Then you get to multicellular organisms. So we don't know how long or how common that is. And then there's the whole, how long does intelligent life last? And we have no idea about that. So there's a few terms in the Drake equation that we know. The rest of them are essentially completely unknown. And when you multiply together a whole bunch of completely unknowns, you've got still completely unknown. So we really don't know. It's a handy way to think about how difficult the problem is, and it reinforces that the problem is incredibly difficult to understand.
Yeah, that's the million-dollar question, isn't it? I think there's two components to that, probably. So the Drake equation has 9 components to the equation, I think, something like that. And each one of those has a lot of unknown variables. So, if you say you're off by a factor of 100 in one of those variables, and maybe one of the variables is actually, how many stars are in the universe, we might be off by factors of billions. If you have 9 variables and you add those all up, that's a big numbers game. The other thing is that we occupy a very particular time slice. And so, if you think of our capacity to generate a radio signal that can be beamed across the universe, that's an infinitesimally small sliver of time, right? We've had an advanced society since 200 years or something, or whatever. And it's nothing. The universe is 13.7 billion years old, right? So what's the chance of being at the right place at the right time to intercept a signal that sweeps by 200 years, right? So it's just a numbers game.
Beyond our solar system, the next location for habitation is our nearest stellar neighbor, Proxima Centauri. Here, several planets have been detected, some in the so-called habitable zone around their star. Sending a probe to the nearest exoplanet is a daunting challenge, but not impossible, even with today's technology.
So even getting a probe accelerated up to a tenth the speed of light would be extraordinarily technically challenging. And that would then take 40 years to get to Proxima Cen. The difficulty being that it would have to be extremely small to get it accelerated up to that velocity. So it's not entirely clear that it would have a big instrument package on it. The other problem is that it wouldn't actually contain probably an engine that would enable it to slow down. So it would essentially fly through the Proxima Cen system at the tenth the speed of light. And so it would essentially take a bunch of pictures very quickly and try to send some information back, and then you'd have to wait another 4 years for that information to get back. Look, I think it's an interesting idea. Whether it's a cost-effective use of our time, I'm not entirely sure. I think probably rather than trying to work out how to make a very small probe accelerated up to that velocity and then fling it at Proxima Cen would be developing the techniques for building space-based, the very complex space-based telescopes that would enable you to block out the light from Proxima Cen and try to actually image the planet itself, to do direct imaging, unlike Doppler wobble, unlike transit searches where you're only seeing the star and the effect the planet has. Try to actually see the planet itself, then try to get spectra of that planet to understand better what's actually going on its surface.
It appears, with all the evidence at hand, the sum of the Drake equation would currently be 1+. We are the 1, The plus is the possibility of technological intelligence within our stellar neighborhood of 1,000 stars. The odds are not good. It's not a question of the available environments, of which there are many. It's to do with the timing. Our time slice within the immense age of the universe may well leave us bereft of company for thousands of years, before our emergence and after we are gone. Fossil fuels, coal, oil and gas, helped create the modern industrial world. Energy generation is the backbone of modern civilization, providing for industry, heat and light and high living standards. 200 years of combustion emissions, in particular CO2, are inducing high-speed climate change such as we have never seen. To mitigate this climate emergency, we must use all of the tools at our disposal. One critical technology is nuclear energy.
The global gold standard for climate projections is amassed by the Intergovernmental Panel on Climate Change, UN body. Now, they're not responsible for the climate modeling or even the observations or all the science behind climatology and climate science, but they are the world authority for examining the uncertainties associated with the different projections and the trends. And one thing we've noticed from the IPCC reports is that they come out sort of every 5 years, and every one is worse than the last one. And the world is currently tracking pretty much at the worst case scenario or above for every time one of the reports comes out.
Intensive observations have revealed consistent cryosphere reduction and global temperature rises.
Right now, we're averaging about 0.2 degrees per decade increase, varying between 0.1 and 0.3. And if we continue at the current rate, which we have been doing for some time now, we will achieve 1.5 degrees by 2030. And at least 3 degrees by 2100. So most scientists in the field are pretty much of the opinion that keeping it to within 2 degrees by the end of the century is pretty much impossible by now.
Moves to reduce carbon emissions to counteract climate change and its effects have been slow.
It's vitally important, and it's getting more important with every passing day at the moment because we just aren't doing enough of it soon enough, and it's been that way for quite a while. So when I was setting the context for my energy research, I went back to look at what our process has been over 30 years really of being alert to the challenge of climate change. And you can really see that all of our major institutions, governmental, intergovernmental, have been, in a sense, in a form of denial over just how big this challenge is, which you can sort of sum up with needing to provide clean, decarbonised economy for a 10 billion person planet with everyone at high living standards. And we just have not gone about the challenge in appreciation of that at all. And it shows, because now we're at 415 parts per million CO2 concentration. When I changed my mind on nuclear power, it was only about 390. This is really concerning. So we are on track to change the nature of our climate in this century in ways that are really going to change the way we occupy this planet for the much harsher and the much worse. So we have a big job in front of us, and people are still realizing just how challenging that job is.
Some obvious results: the acidification of our oceans, a rise in ocean levels, and it's becoming a runaway effect.
Well, oceans are probably going to increase anywhere between 0.2 and 0.5 meters by the end of the century, although that's contingent on a model of gradual melt. And as we're seeing now from Arctic sea ice and Greenland ice sheet, that it's probably going to be more of a catastrophic shift. Also, the paleo data from mass pulses of ice and fresh water through the different interglacials and glacials events over the last 200,000 years or so show that it wasn't gradual. So we had these huge pulses, especially coming out of the North Atlantic, that changed sea levels in terms of meters in less than a few centuries. So we could be seeing a lot more. But unless we massively reduce our emissions, and we haven't been able to do that at all up to date. I mean, yes, we've increased renewable energy substantially, but our demand and our production of fossil fuel-based energy in particular is keeping way ahead of what any gains we're making from clean energy sources.
Another consequence of burning coal has been air pollution, and its effects on populations have been dramatic. Estimates suggest that in India alone between 2011 and 2012, there were 111 coal-fired power stations. As a result, the country registered between 80,000 and 115,000 premature deaths and more than 20 million asthma cases. Humans aren't the only species threatened.
Actually, these days we're getting a much better handle on the effect on life, from plants to insects to big animals, including us. And that's partially from better predictions and also better observations of what's happening today, but also looking into the past. Now, what we do know, at least over the last few glacial cycles, so going back, several hundred thousands of years, that when the warming events came, that's when we were seeing the big extinction pulses. So losing the mammoths and the saber-toothed tigers and the diprotodons in Australia, that actually was, in most cases, synonymous with a warming, or in the case of Australia, drying event, as well as humans coming in. So it was kind of like a 1-2 punch. So, and that was sometimes over the course of thousands of years. Now, we have a vastly increased rate of change, and there is adaptation to a certain extent, but in the areas where the thermal range is quite low, for example in the tropics, even though it's on average higher, the variance is quite small, sort of day to day or season to season. That's where we're likely to get the biggest extinction rates. Now, we've done some other modeling along those lines that makes it even scarier, because most of the models are contingent on exceeding thermal thresholds. So this thermal tolerance of species X, once you surpass it, the species goes extinct, and then you look at the species specific thermal tolerances and you calculate how many you're going to lose. If you do it that way, you're looking at about a 5 to 10% loss by the end of the century on current projections. That's just from climate change. So that doesn't include anything like overexploitation or deforestation or invasive species or pollution or anything like that. So this is just in addition. But ecology doesn't work like that. So what happens is you get one species that will depend on a whole host of others. For example, it's simply a specific pollinator to a specific type of a plant or tree or something like that, or a flower. When the pollinator goes extinct, the plant does, or the other way around. Or I think of a predator and specializing in particular prey. If the prey goes extinct, the predator goes extinct. We call these things extinction cascades. And we just did some work last year that showed that not taking into consideration these extinction cascades underestimates the effect of climate change by up to 10 times in a warming scenario. Not only that when you try to break the system, and these are virtual Earths really that we're creating, when you try to make the worst case scenario to get the fastest extinction rate to total annihilation, it pretty much mimics exactly what's happening with the heating scenario. Even I, who receives terrible news every day, was absolutely shocked by that kind of information. We have no idea how bad it's going to be.
But left unchecked, climate change will have massive effects on us.
Well, there's quite a lot to that, obviously, because it affects human societies in so many different ways. There's obviously the direct effects like heat waves. In fact, in Australia, the biggest mortality type from a natural disaster is not bushfires, it's not cyclones, it's actually heat waves. More people die from heat waves in Australia than any other natural event. Flooding, doesn't matter. So that's a direct effect. But we also have so many indirect effects, and one of those, of course, is food supply. Now, a lot of people might be thinking we're sort of at that optimum yield kind of threshold for most major crops around the planet. That's possibly true. There could be more intensification, but generally speaking, if you look at like some of the major crop types, like wheat, for every 1 degree of warming, you get about a 6% reduction. Now that's considering a linear prediction, which is unlikely to be. But water is another issue. I mean, we have already halved the water availability per person across the planet since the 1960s. So that's, of course, a function also of population growth, but water is becoming scarcer and more restricted to particular areas. So if we get major water emergencies happening in places like the Himalayas or that entire region of the subcontinent, you're looking at 2.5 to 3 billion people that depend on that water source that will suddenly have to find water elsewhere. It's already starting to happen in India. Australia is no stranger to water shortages. We are the driest inhabited continent, and yet we still choose to grow things like rice, and we can't seem to manage our largest river very well. So, if we can't even do it, it's unlikely that many other countries will be able to. Not only that, human population will grow by about 35% by 2050. So we're gonna hit about 10 billion by 2050. We're likely to exceed 11.5, 12 billion by the end of the century. And because of most of that growth is in developing nations, we're going to actually have to double our food supply by 2050 just to keep pace. Because many of the developing nations are eating more meat, which is more both water and food intensive. And that brings about an associated lift in emissions. So, you think about emissions from electricity production only represent about 1/3 of the total emissions of a country. Agriculture is another third. So we have to get the agricultural side of things from a climate change mitigation in addition to just electricity supply.
Scientists and engineers have been growing more concerned every year.
The Nuclear for Climate initiative, that was an idea that was started by the American Nuclear Association with the French Nuclear Association, SFN. And it was a terrific idea that came to pass in 2015 at a conference called ICAP in Nice, where delegates from 36 countries around the world signed to commit their societies to pursuing nuclear for climate change reduction. And that represented memberships of about 50,000 scientists around the world. And we all signed that agreement on behalf of our respective societies, and it's proved to be a very good vehicle for getting on track with addressing the world's climate change problems.
There's not going to be a silver bullet in climate change mitigation. We are going to need everything available to us, the whole suite of solutions working and deployed in a fashion of some urgency. But of the technologies we do have available to us, nuclear technologies as a group, by far and away, will make the biggest difference and are able to make the biggest difference. We already have living proof of nuclear technologies decarbonising whole power sectors for developed economies. This is crucial, and that we would overlook that is distressing almost, as we have this challenge in front of us. So we know they can provide the electricity, they can provide the heat to decarbonise a lot of the industrial sector that largely runs on burning gas and coal. Solar panels and wind turbines just don't get into that sector at all. With that heat and power, we can desalinate water, we can manufacture fuels, we can power food production, and we can do all of these things from a very small amount of land, with a very discrete amount of fuel, with a waste product that stays fully in our control. That's a remarkably powerful solution. It's probably our biggest single lever. And so while I am absolutely across and supportive of all the technologies we have in front of us, I believe the potential behind nuclear technologies is second to none. It is going to need to be a big part of a decarbonised future.
The world needs energy, and fossil fuels have to be replaced with renewable, clean energy.
It's not just about coal. We have the need to replace petroleum fuels in our light vehicle car fleet and in our heavy vehicle car fleet. We need to be putting more electricity into our train systems, not diesel. We need to be replacing metal smelting with hydrogen reduction as opposed to carbon reduction. So there are a whole suite of industrial processes and transport processes which will take more reactors in the future. And there will be different reactors. There will be high temperature reactors which are able to address these industrial processes. One, for example, such as the terrestrial energy reactor being developed, which is a molten fuel type of reactor, a molten salt type of reactor. They've got terrific advantages because those reactors do not operate at elevated pressures, and they operate at elevated temperatures, able to take part in industrial processes which need elevated heat.
Yeah, I mean, one of the major limitations of non-nuclear clean sources of energy like solar and geothermal and wind is that you have to put them where the sunshine is and where the wind is and where the geothermal is, which means that you need a quite a vast transmission network, and it's usually not in the places that have the highest demands. Whereas something like a small modular reactor, you can stick next to the highest demand source of electricity or industrial heat. That's another thing that nuclear does provide is the really, really high temperatures we need for industrial processes that we can't achieve yet, at least with renewable energies. So you could reduce your costs in terms of transmission by placing these anywhere you needed them, and really get rid of the transmission requirements and the loss of energy that you get from transporting it over long distances.
Frankly, there's often a bit of a trade-off. We look at wind farms, and if there was an overriding societal benefit in putting them up and down the Great Dividing Range, then I would be convinced that that would be a good way to go. But unfortunately, what we're really doing is industrialising our landscapes, putting in a whole bunch of excessive pump storage, a whole bunch of hydro onto dams, and I've been involved in some of the world's largest hydropower projects in the Mekong system in Vietnam, has a tremendous environmental toll on those local environments. And so part of getting involved in this issue was looking at the true ecological benefit of different power systems. And we come back to the environmental footprint, if you like, of nuclear versus virtually every other power system. Nuclear uses very few materials. It can last up to a century. The systems, when deployed, we have wind, which uses around about 13 times more materials than nuclear power stations. PV, similarly, about 10, 13 times more materials than in a nuclear power reactor. But that doesn't even account for this promise that people are talking about of using battery storage. And when we start going down the route of using very expensive batteries with all the chemical processes involved and their low life, because most batteries are flat out lasting for more than 5 to 10 years and need replacement, we're going to see tremendous pollution issues with the industrialism around the replacement of battery systems. And we're going to see those sorts of systems have around 20 or 30-fold the materials use of nuclear power plants. There's nothing cheaper in Australia than coal. We've got to be clear about that. What we are seeing, however, is that as people try to put renewables, intermittent sources of wind and solar out into the network, we're seeing, and as that expands, or should it expand, we are going to see a steadily growing system of backup systems to enable wind and solar to work. That will include, as we've discussed earlier, things like gas turbines with all of their problems. So we're going to have a whole suite of underutilised equipment. The grid that's created around this will have the same capacity factors as the generators, so it'll be down around 20 or 30%. We're going to have the same problems with whatever storage devices we're having. And it will be the low use, the low average use of all of these bits of kit, which will increase the cost. And so the future, with an increasingly renewable system, will be more and more bits of gear that are not operating at their commercial efficiency. What we get with nuclear is we get a compact system. We can maximise the use of our existing grid. We can maximise the use of our existing cooling water resources, of our transport systems, of our rail. All of this equipment that we've currently got, we can take the greatest benefit from. And of course, the reactors will operate at 90% of the time, so they'll be very continuous. So while the individual cost is high, it's reduced in a system effect by their continuous availability without requiring all of the underutilised gear.
So just about all of the nuclear power that's in operation in the world today runs on the same general fuel cycle and principles, which is ceramic, uranium oxide, fuel pellets, generally in a metal sheath, using water as a moderator and coolant to create steam, to create electricity. Now, the very first generation of those power plants, Generation 1, you could think of them as somewhat upscaled versions of what was on submarines previously for the Navy, brought on land, introduced into power production. They were smallish in size and they ran for some small number of decades, but not all that long. The second generations, where they really upscaled those designs, made them a lot bigger, built a lot of them, and that's actually the vast bulk of the nuclear power in operation today is Generation 2. Same basic fuel cycle, but they were turned into a commercial proposition. And they have been very successful. So around the world where they have been deployed, we generally see very reliable, stable power, which is operating at a very good price in the economies that are using it. So effectively, the workhorse is the global nuclear sector today. In Generation 3 reactors, it's the same basic fuel cycle principles, but the engineering is being simplified a bit. So fewer active systems, more passive systems for safety, slightly simpler design. There aren't actually many of those reactors operating in the world today, but the ones that were constructed, particularly in Japan, were built very quickly, were built on schedule, and again operate really successfully. And then we get into Generation 4 reactors, and that's where the palette really opens up into a lot of new and exciting technology choices.
Okay, the world view, what we're seeing internationally. If we look at reactor suppliers that are doing quite well, we've got the Russian industry. It's growing, and we're seeing, for example, 6 new reactors going into Egypt. We're seeing reactors being built in Chile by the Chinese. We've got new reactors going into Pakistan by the Chinese. We've got new reactors going into Bangladesh by the Russians. So around the world, in parts of the old Eastern Bloc, as we used to call it, and in these other smaller nations, we've got Chinese and Russian industries are serving those markets quite well. In the United States, we have the older fleet that existed, and that's coming under increasing pressure by cheap gas within that nation. And so nuclear has to compete under a regulatory regime that's expensive, with cheap gas entering the marketplace. But the new administration over there, and actually the old Obama administration, were looking at putting programs in place to encourage the development of new reactors. And so we have terrific new reactors like NuScale, which is a small modular reactor, which can be built in modules up to 600 megawatts.
That is a light water reactor. It's using the same fundamental technology and fuel cycle, but a very shrunk down size, a small array of up to 12 small reactors, making it very nimble and able to load follow with very high outlet temperatures. And that is in licensing right now with a customer ready at the end of that. That's very exciting. If you look at the terrestrial energy integral molten salt reactor from that Canadian outfit, it is going through the Canadian regulator. It is in stage 2 of its pre-licensing review. It is moving toward build in the 2020s. So I think we need to track these things one milestone at a time and treat them in that way. But now I think we can say with confidence that it is a 2020s outcome that we're heading towards. That is going to offer particularly advanced economies that aren't building massive power plants anymore, an extremely good option for swapping out their existing fossil fuels and incrementally but swiftly changing over and transitioning to clean energy sources.
The real powerhouse we're seeing in reactor development is in North Asia, particularly South Korea, where we've seen the nearing completion of 5.6 gigawatts in 4 reactors in the United Arab Emirates. And they've done that in the harshest climate in the world for any form of construction. And they've proceeded with discipline, and they're getting that project over the line. So while we're seeing some political pushback, and we saw President Moon of Korea, for example, he got elected on the basis that he was going to wind back the program, we're now seeing polls in South Korea of 70% of the people in favour of nuclear. After his election, we saw a citizens' jury determine in South Korea that the reactors at Shinkory 5 and 6 should continue to be constructed. There is what I would call pushback, because the political processes we often see that a politician will take policies, polarised opposites to the previous administration to curry favour. That's unfortunately the nature of politics. We saw that happen also with President Macron in France, where he was initially elected on the basis of tampering back the French nuclear fleet, and now we've seen a report come out about 2 weeks ago where they're advocating the building of 6 new reactors, and also the resignation of their Energy and Environment Minister over that sort of issue. And so the President of France has now realised, for example, what a tremendous benefit low carbon nuclear energy is in Europe, and he's contrasting that with the appalling situation you've got in Germany, where they're winding back their nuclear fleet. Their emissions are plateaued. In fact, they may even be slightly rising. They're certainly not going to meet their targets. They've got lignite mines now being developed, and their emissions are up around the 500 grams per kilowatt hour compared to the French emissions down around 40, or about a 12th of the German emissions. And so around the world, we do get reassessment by people, particularly as a result of Fukushima. But then we see changes in resolve, and we've seen that now going on in Taiwan, where they're now reassessing their decisions and in favour of keeping nuclear.
Well, Germany is the classic case of what not to do. The Energiewende was a massive failure. I mean, they're currently spending about €500 billion to increase their renewable energy transition without actually cutting any of their emissions, because they chose to shut down nuclear and opted for lignite as base or the primary source of that electricity. So we absolutely don't want to do what Germany is doing. I mean, even there's a lot of pressure in places like Japan and South Korea to do the same thing. When you've got demonstrable successes like France and Sweden and Ontario in Canada. And Ontario is really the kind of the pie in the sky example of what we want to be able to achieve. Yes, they have lots of hydro as well, but they have some of the lowest emissions on the planet in a very wealthy and well-functioning society in the developed world that is really, I think, the icon we need to be striving for. France, for example, is another one. I mean, the one thing you think about when you think about France is gastronomy and wine. Well, not one thing, several things. But we generally don't think that image has been ruined by the fact that they are some of the most nuclearized countries on the planet. So I think that having that kind of demonstration that it works is exactly the reason why we shouldn't be shutting them down. We should be putting more in. If you look at places like China, India, much of the Middle East, they're putting in nuclear at a rate that just boggles our minds. And they're doing it because they need to. You can't breathe the air in some of these countries. So that's one impetus. Massive burgeoning development and consumption means that they need lots of electricity. So, you know, if these countries are going down that route, we should be considering it as well.
In total, there are 450 nuclear reactors in use, supplying only 10% of the world's electricity. 50 reactors are currently under construction in 15 countries. Most are of the advanced passive design.
One of the tremendous virtues of the APR series of reactors that the Koreans have developed is that the AP stands for Advanced Passive. And what we have seen through what we call Generation 3 and Generation 3 Plus reactors is for the ability of these reactors, if they come under a critical departure from proper operations, is for them to be able to shut themselves down passively without human intervention. And we also have other benefits in those reactors, such as pressurized core injection. So water can be driven into the reactor, or the entire reactor zone can be flooded. And that would prevent issues such as that which happened at Fukushima, for example. So there are a significant suite of new advances that are going into the AP series of reactors that did not exist in the earlier ones and would be incorporated into the types of reactors that would be used in Australia.
The existing Generation 2 and 3 reactors working in the world today do the job really well, and they've done it well for decades. But why would we want Generation 4 reactors? Well, there are some real advantages that are coming. With some of the advanced fuel cycles, they become what's known as walk-away safe, or inherently safe, meaning it literally, by dint of physics, cannot have a runaway overpower event. So they are effectively meltdown-proof. Even if you were to simply switch everything off and walk away, they will sit stable and calm. That offers a few advantages. It de-risks the projects hugely in terms of their siting. They require smaller emergency planning zones. They can be more comfortably embedded in industrial settings. They can be more easily connected onto grids. The materials become a lot lighter. Many of these designs will operate at atmospheric pressure. So rather than pressurizing water very, very hard as its coolant, because they're using advanced coolants, they have a much lighter build. There's no pressure containing energy, so they become simpler designs. Where I really believe all of that is heading is we need them cheaper. It is absolutely essential that we are able to make nuclear power plants cheap, scalable, swiftly deployable, really high quality control. So moving from a construction paradigm more to a manufacturing paradigm, much in the manner of solar panels that can be turned out from a factory and quality controlled. We do need more of that paradigm for nuclear power. Now, that is not to say that large reactor build projects can't be successful. They can. But these Generation 4 reactors are going to be able to, I believe, turn out at the scale we need to get at that huge climate change mitigation challenge in the way we are going to have to. Now, one type of Generation 4 reactor that I'm particularly excited about recycles used nuclear fuel. That is quite game-changing for me. that was a huge part of my journey from anti-nuclear to pro, is understanding that the thing I had thought was the biggest problem for nuclear technology fundamentally didn't need to be a problem at all. So there is a way of using nuclear power reactors to turn all of the existing nuclear waste into a form of new fuel. So we get about 20 times more energy out of the same existing mined fuel rods that we already have sitting in canisters today. I find that incredibly powerful. In the process of doing that, the waste that we are left with is much smaller in volume and dramatically shorter in half-life, only about a 30-year half-life. And so that changes the entire paradigm of waste management for nuclear technology as well. So the promise of that technology, which is well established, exists in a commercial form, but is not yet licensed and being built, for me offers tremendous confidence that we can go forward with this technology and understand that we're doing truly a very sustainable thing for the future. So we can use a process known as pyroprocessing, where we essentially snip up those fuel rods, reduce them into a liquid electrolyte, run electricity through them, separate the elements into a form of adequate purity. We put aside the true waste product, which is only about 2 or 3% of the fuel rod, and the remaining balance can be refabricated into new fuel rods. And using a metallic fuel alloy and an advanced fast reactor, those fuel rods can breed and create more fuel on every occasion. And we put it into that closed loop and progressively recycle all of that fuel rod. And that waste product that comes off the side, known as fission products, only has a half-life of about 30 years. So suddenly my mind was a little bit blown when a challenge went from things with 24,000 year half-lives, so 250,000 years, to something with 30-year half-lives, or 300 years of management. Suddenly that's a completely different paradigm that opens up a huge range of options for responsible waste disposal, not least of which getting 20 times more zero carbon energy from the same fuel we already have. Now, the power of this can't be understated. It really means that if you take all of the existing used nuclear fuel around the world, if you also add the depleted uranium that came from the enrichment process, there's enough existing fuel to power that 10 billion person world at high standards for several hundred years right now.
It's an effective argument to take to the politicians.
Well, I'm a little bit jaded being a scientist and having interacted with politicians for many years. If anything, politicians listening to scientists is getting less likely and then more. So in by itself, even the climate emergency and more scientists backing these kinds of technological solutions, or at least contributions, isn't going to be enough. I think we really have to get better at marketing the message and understanding the pros and cons a little bit more, and trying to take the emotions out of the rational decisions. Because when you come down to looking at everything, including not just the costs, but the safety and the economics of the long-term effect and obviously the reduction rates in emissions, they speak for themselves. And we have to get over a long-term negative association with the N-word and try to show people that, really we don't have a choice. I often say to people, I said, look, even if we were implementing Gen 2 kind of technology, so going back to the Fukushimas and the Chernobyls, or even before that, and even if that was all that was available to us, the magnitude and the emergency of what's happening today in terms of climate alone means that we could, even if we had meltdowns, it would still be worth it, because on average, we would still be ahead. So, of course, we don't need to rely on that technology, so it's much, much better. But I'd be willing, I have a small bit of land in the Adelaide Hills. If someone said to me, we've got a small modular reactor and we need some space to put it, I'd put my hand up right away. And I run a farm. So, it's to that extent that we need this kind of technology.
And there have been other precedents for that type of thing around the world. In the 70s to the 90s, 1970s to the 1990s, France built 58 reactors over a 22-year period. And they did that before the advent of the personal computer in the workplace. So they were really ahead of their time. We would replace the coal-fired power plants that are going to retire between now and 2042. That's 20 gigawatts of energy will be departing the system, and we would replace that with 20 gigawatts, or roughly 20 power reactors across Australia. So that would be an ongoing program of construction.
Making a concerted effort to disassociate the N word for nuclear weaponry from the N word that is nuclear energy is a really important part of that, and convincing people that it's safe. People don't process risk in a probabilistic sense. We're not, robots. Most people have to train to do probability theory, and to think about the probability of there being a problem for a particular technology or not implementing a particular technology. It's hard for people to fathom without really good metaphor and analogy and a lot of information available to them.
I am heartened that it appears to be possible if we look at places like the United Kingdom, if we look at places like Finland. We do see pretty good, strong, growing political consensus around climate change and energy that have become technologically inclusive. So there are models and templates out there for this type of depoliticisation of nuclear power. It will be hard. It takes people to speak up and set a good example. I try to set the example from the point of view of one of those people who is so concerned about climate change, trying to build bridges, trying to provide, I think, particular for other people to see that I can be a supporter of these technologies, and that doesn't mean saying goodbye to these environmental values that I hold dear, because it doesn't. It's actually remarkably, incredibly consistent with those environmental values. And I think once people can feel that, they feel a lot more confident about getting on board and having a depoliticised discussion about nuclear. It's a big challenge, and we're challenged every time we speak and open our mouths on this topic to try to move it forward and not fall back into old patterns and old habits.
Well, I think if we're looking for leadership in this kind of technology, we won't be finding it from our politicians. But we need the politics to be on side, because currently nuclear is illegal for electricity production in Australia. And that's in a number of acts. So it's in the Environmental Protection and Biodiversity Conservation Act, it's in a number of other acts that we'd have to rejig a bit of our legislation. That's not that difficult, as it turns out, but we would need to deal with the legislation and the politics just to make it legal. But if we're waiting for politicians to do that for us, it's not going to happen. I see, obviously, the younger generation as being the key to almost every issue that we have environmentally or otherwise today. But it has to be across society. I think that if we are going to get acceptance of implementing nuclear, for example, in Australia, we need to have that across the board. Yes, more educational material, more training, more promotion, and certainly more discussion. A lot of people, including myself, have tried to make awareness a bit more about these issues, and there have been more and more bits of information that are helpful. Obviously, something like this particular film is going to be useful for people, and getting the message out. And it's happening. It's happening slowly. I mean, you don't get a culture shift in a few years. Often it takes a generation or two. But the more material we have and the more evidence we have are great things. And I guess that's the first step.
What of new fuels being developed like hydrogen?
I mean, hydrogen has certain advantages and disadvantages. For example, it's very difficult to move. So it's kind of hard to bring the energy to where it's needed. And electricity transport and transmission are some of the key limitations of feasibility for rollouts of all sorts of types of alternative electricity production. That includes solar and geothermal and wind. So in certain regions, the right mix of fuels, including hydrogen, would be different. And that's the other thing too, is that all the sort of optimal mixes of nuclear, hydrogen, solar, geothermal really depend on the region, and they're never the same. So would we have a hydrogen economy? Probably not. Could we include a much higher proportion of hydrogen in our economy? Absolutely.
And the promise of fusion power.
ITER is an experiment to try and demonstrate that you can operate and maintain that plasma for periods of time necessary to produce fusion power. So there's various concept designs that would generate fusion electricity. There's a European demonstration power plant design. China has one that I talked about. Japan also has one, as does the US. And Korea also has a K-demo concept. So the idea of ITER is to generate the science information that's necessary to operate and control in a steady state fashion a fusion power plant. So ITER, when I say operate and control, what I mean by is that we haven't run a machine in a burning plasma configuration before. So we really need to explore and understand whether or not the machine will run in steady state, whether or not the alphas will remain sufficiently confined to produce a self-heating plasma, whether or not the plasma will be stable over a long enough period of time to produce power. So we need to answer all of these science questions first. But in parallel to that, there are concept plans to build demonstration power plants. And the timescale for that evolution, if you look at various different roadmaps, ITER will be sort of operational, producing high-performance plasmas mid-2030s. There's concepts to develop or deploy demonstration power plants in the mid-2040s or 2040 or thereabouts.
Those sorts of timeframes mean we need to keep developing our renewable energy resources. We need to keep deploying wind power and solar power. We need to keep using the existing commercial nuclear technologies we have. We need to keep open and operating the existing nuclear power plants we have. We need to extend their lives. We need to maintain our existing fleet of clean energy to keep those carbon emissions down as low as possible. The time for waiting for the thing to come and save us all is long gone. We need to be using everything that we have right now. The designs that have been commercialised today based on advanced nuclear fuel cycles but not fusion promise really material, important improvements on what is already an excellent solution we should be implementing. And let's remember that it is actually through that healthy, strong nuclear power sector, through that food chain, if you like, is more supportive of advanced nuclear research in every respect. If we want to see fusion in future, great. Well, let's have a healthy nuclear sector today as we decarbonise. But particularly, let's not put our climate at risk waiting for a perfect solution. We have what we need right now, and it's time to put it into practice.